Well, thank you all for coming. I hear this is the first specialist discussion that the RAS is having back in person after the pandemic. So that's pretty exciting. So the topic for today is going to be solid liquid interactions in deep planetary interiors. We've got a really great and exciting lineup of speakers and two fantastic invited speakers. I'm sure you're all very much looking forward to hearing from. And we've got some posters upstairs in the library as well. A little bit of housekeeping before we get started. So this meeting's recorded. The recording will be kept by the RAS, and if anybody has any objections, we can make edits to this before they upload it to their YouTube channel. Fire exits, essentially just go out the way you came. If there's any problem, there'll be a fire marshal, but just head out of the courtyard the way you came and you'll be directed. Toilets, for those that haven't been here before, are under the stairwell downstairs, and there's also one on the second floor. What else? We'll be doing posters over lunch. It's going to be a bit of a tight schedule, so if you're presenting a poster, make sure you get something to eat as well, because we're going to be a bit short on time. We'll break for lunch at 12:50 and restart at 1:50. Talks will finish at 3:50, and then we'll have a bit more poster chat up in the library again. Yeah, and with that, I think that's all I want to say is housekeeping. And Dario, do you want to start introducing our speakers?
Hi, my name is Dario Alfè. I'm going to chair the session of the morning. So it's a pleasure to welcome you all. Apologies to the speakers. I will probably mispronounce their name. They will. No, my name is mispronounced anyway all the time. So hopefully this is not revenge for that. So the first speaker is invited speaker, Tina Ruckriman. Freezing metallic cores, where do all the solids go?
Yeah, thank you so much, Dario. That was perfectly pronounced, but I just saw that the the subtitle was interesting. I'm going to talk about core freezing today. And when I was thinking about the title of this talk some weeks ago, I do have to say that I immediately felt this question of where do all the cores go, because it really feels like that when you have like new data on temperature or core temperature, and you try to figure out where stuff is freezing in the core, and then you're sitting there, no worries. And you try to figure out where stuff is freezing in the core, and then you're really sitting there, is it rising, is it sinking, does it dissolve at some point? Thank you so much, Brent. And is there a pointer somewhere or not? Or if not, it's also fine. No, I'm just a little bit more. So yeah, I can do that.
Good catch. Yeah, perfect. Thank you.
Yeah. So, but I think I'm going into too much detail already, and we probably should go bit by bit. So this statement, cooling planetary cores and its consequences matter, is actually a statement by Dave Stevenson. He said during a meeting at the Keck Institute really some years ago. And but I think it's a simple and beautiful statement, which is absolutely true. So why is it true? If we cool the core, there is, of course, one very obvious implication. It's that we reduce the temperature, so what we would call secular cooling. And the degree of heat that is extracted from the core is important because it tells us what the liquid in the core is doing. If the heat that is extracted from the core is less than the heat that can be theoretically conducted along the core adiabat, then we say the core is stably stratified. Of course, this is overly simplified because we know that not immediately the entire core is stably stratified, but only a portion of the core will be initially stratified. And then depending on the degree of subadiabicity of your core heat flux determines how thick the stable layer is. If the heat that is extracted from the core is larger than the heat that can be conducted along the core adiabat, then we will have a thermally convecting core, which gives us large-scale motion. And this in turn is important because it will enable the system to likely create a global magnetic field. because this needs high enough velocities and large-scale fluid flow. And we know that the metallic cores of terrestrial planetary bodies have contain a lot of iron, which is electrically conducting. And if this is moving, magnetic fields are induced. So the problem with thermal convection is that if we have really low, really high thermal conductivities, then the efficiency is rather low because a lot of heat can be conducted along the core adiabat instead of being convected. However, the discussion on thermal conductivity is a constantly ongoing discussion. The value is rising, it is decreasing. So this is always like up and down. And I think it will be a matter of years maybe until we finally settle this issue of the thermal conductivity of metallic or iron-rich cores. The other direct consequence of cooling planetary cores is that you will freeze core material at some point. And this is going to be the focus of this talk. Light elements are really important in this matter, because they can create strong buoyancy forces, which are in turn important for creating large-scale fluid motions, which in turn are important to create global magnetic. A very common example is sorry that you cannot fully see that, is the growth of the inner core for Earth core. This is probably what most of you are familiar with. We know that solid iron is crystallizing at the bottom of the core. It is heavier than the surrounding liquid, it would stay there. But during the crystallization, the sulfur, or it's not sulfur in the Earth's core, but the light alloying elements, so not mainly sulfur, but the light alloying elements are expelled to the outer core, creating a light layer on top of the inner core boundary, which is gravitationally unstable and will tend to overturn in the outer core, creating large-scale motions. What I want to convey with this talk is that there really can be a diversity of freezing cores. So for a really long time, the community has only talked about inner core growth whenever they also did the models for other planetary bodies, terrestrial bodies like Mars, Moon, Venus, not so much because we don't know what is going on Venus. It's likely too hot to create a magnetic field. But anyway, so mostly we were talking about inner core growth. However, the location of core freezing crucially depends on the slope of the liquidus temperature compared to the core temperature. So the gradients are important, and I will try to illustrate that with the two panels or sketches shown here. On the left-hand side, you can see a sketch which would lead to top-down core freezing. So it's a really oversimplified sketch, but it's going to convey the message. You can see temperature on the horizontal axis and pressure on the vertical axis. And you can see that in both panels, the pressure gradient of the liquidus temperature, which is dashed line, is smaller than the pressure gradient of the core adiabat, which is solid line. And if this is the case, both temperatures will first meet or intersect at the core-mantle boundary, given that they are monotonously increasing over the pressure of the core. And the implication then, or the question we can ask then is, what is the density of the core material that is crystallizing? If this material is heavier than the surrounding, the material will tend to sink. And how exactly that looks like, I will try to explain in the next slides. And if the material is lighter than the surrounding liquid, it will tend to stay where it crystallized, meaning directly at the top of the core. The other scenario we can envision is that the pressure gradient of the liquidus temperature is steeper than the pressure gradient of the core adiabat or the core temperature. It doesn't have to be an adiabatic temperature. And in this case, we will have freezing from the bottom to the top, meaning both temperatures first meet at the core center. And as soon as the core temperature drops below the melting temperature, material crystallizes or freezes. And if this material at the bottom is heavier, then it will just stay there and will create something like an inner core that we know for Earth. And if it is lighter than the surrounding liquid, complicated things can happen, but maybe it will tend to rise towards the top of the core. Let's go one by one a little bit through these freezing modes. So growth of an inner core, as many know, many of you probably know that we can go through this rather quickly, I think. So you can see the sketch here. It always contains two panels with sulfur content and temperature, sulfur content being on the left and temperature on the right-hand side for these panels, and versus depth of the core, CMB. Here is the core-mantle boundary. And then you have three panels, and you they depict the progression in time, or you could also say the degree of cooling. So the leftmost panel is hottest in terms of temperature, and the rightmost panel has the lowest temperature. And what I already told you is if we now stick to the iron sulfur system to simplify things a bit, but it doesn't have to be iron and sulfur. It could be other components. They simply have to behave similarly in terms of melting temperature and density. And what you see is that as soon as both temperatures intersect at the center, you will create a solid iron core. Of course, melting temperature in the solid iron core is the melting temperature of pure iron, because in the iron sulfur system, sulfur is not partitioning into the solid phase. It's mainly partitioning into the liquid phase. And if you progress in time and you cool your system, you will further grow your inner core, always putting all the light elements into the outer core, which creates large-scale fluid motions because it's a gravitationally unstable situation. And you go on and on and on. And you can do that as long as you don't reach the eutectic concentration. Once you reach the eutectic concentration in the binary alloy, you will freeze the entire core. And convection can take place as long as there is sufficient energy, meaning as long as the geometry allows for it. If the layer becomes too thin, convection might not be feasible anymore. And of course, if the core is entirely solid, it might also not convect. Not in the way, at least, we want it to convect. So then you wouldn't have a source for the dynamo. So this is just still inner core growth. And this is just a sketch, which I actually modified from Chris's and Ann's paper in 2018, because I really like this sketch, I do have to say. And I modified it to be representative of inner core growth. So in our simplified models, because they are 1D models that I will later show, most of the model, all of the models, is that the inner core grows outwards concentrically, and that we have compositional convection in the outer core due to these light elements being expelled. And this compositional convection we assume to be very efficient in mixing the outer core so that it's along an isentrope, meaning adiabatic temperature. And you can see here the different energy sources being released or not consumed in this case, but only released. We have latent heat being released by freezing of the inner core. And then, of course, we have gravitational energy from mixing the light elements in the outer core being released, gravitational energy. And you can see here, without putting too much slides, just a simple setup of the 1D model. You can see temperature along the horizontal axis and radius along the vertical axis. And you can see that both the core temperature is above the liquidus temperature in the outer core, which is assumed to be fully liquid. And then we have the melting temperature of pure iron in the inner core and a solid iron core, where we, of course, don't know if it's fully compacted or not, but depending on the pressure, we can assume that it's almost fully solid. So another freezing mode, as I said, is the growth of an iron snow zone. And again, same sketch, so you don't have to adapt to another illustration. And again, progressing in time from left to right, which is representative of the degree of cooling. And you can see that this time both temperatures first intersect at the core-mantle boundary. And once they do, if the component that is crystallizing is heavier than the surrounding liquid, in this case, it's supposed to be iron, then it's going to sink into the deeper core because it's just heavy. So you have iron crystals, you can imagine, and those crystals will settle through the liquid. That is how we envision the process to happen. Of course, that is extremely idealized. And those crystals will sink as long as the melting temperature is still below the core temperature. The core temperature is still below the melting temperature. As soon as the melting temperature or the core temperature rises above the melting temperature, which can happen due to pressure in those large bodies, those iron crystals will start to remelt. And as soon as they remelt, they create some kind of pool of iron-rich liquid, which sits on top of liquid, which is lighter. This is, again, a gravitationally unstable situation, and it will induce overturning motions. And as long as you cool your system continuously, you will continuously feed this deeper core with iron-rich liquid, which is produced due to the remelting of crystals. And this is now the important point for the iron snow regime here, is that we think that this convection in the deeper core is creating a dynamo below the snow zone. So there hasn't been any really profound work on what the motion that is being induced is in the snow zone by the settling of crystals. And so far, this is only only hypothesis whether this could create large-scale motions. But below the snow zone, where you have this iron-rich layer being mixed into the deeper core, you could probably assume that it's really large-scale motion because it's very similar to what we assume for the inner core growth of Earth, but just turned upside down. But this also means that convection ceases as soon as your system has cooled so far that crystals are forming everywhere, because then you have the snow zone everywhere, you don't have convection beneath the snow zone, and then the dynamo comes to a halt. Again, the same sketch here with the energy sources. In the iron snow regime, we have latent heat being released in the outer core. We have latent heat being consumed below, not in the outer core, in the snow zone. We have latent heat being consumed below the snow zone, where the crystals are remolten or are remelting. And then, of course, we have gravitational energy from the snowing down of iron crystals in the snow zone and the remixing of this iron-rich liquid, which comes from the remelting crystals in the deeper. And again, you can see the temperatures. One important point as well is that we assume for all models equilibrium. And in equilibrium, both of the temperatures in the snow zone will be collinear. And this in turn entails that you have a stable chemical gradient in the snow. So you have the highest sulfur concentration at the top of your snow zone, and it's steadily decreasing towards the bottom of the snow. And of course, below the snow zone, the core temperature is above the melting temperature, and your core is entirely liquid. This is just to show you that there is actually a lot of experimental work ongoing on this system, iron snow system, but I've seen there are a lot of talks this morning that are going to address experiments on various crystallization regimes. So on the left-hand side here, this is an image by a colleague from Dresden who put up an optical experiment to see whether we could create anything like iron snow. And what you can see is that we can actually see equiax crystals in the liquid. And we can see also columnar crystals at the top, which is due to the fact that you have to sufficiently cool your upper boundary. And it's hard to not make some of the crystals stick because it's just energetically favored to stick to an already solid boundary instead of creating free crystals. But the system shows a lot of free crystals actually forming in the undercooled liquid. And down here, you have a mushy layer, which is created by the sinking down crystals. And of course, at the pressures in the laboratory, it's not very well compacting. And on the right-hand side, you can see an image by Ludo, which he will talk about after my talk, an experiment on iron snow on planetary cores, an analog experiment. And I think Ludo will tell us all about it, but it looks really exciting. So last but not least, we have the iron sulfide layer. Again, this time we are again crystallizing at the top of the core. This time the material is lighter than the surrounding liquid and it's going to stay where it's crystallized. And why? Because it's going to stay where it's crystallized, it's kind of forming a cap at the top of the core. But while iron sulfide is crystallizing, it's expelling liquid iron into the liquid phase, into the liquid core and the deeper liquid core. And this liquid iron is again heavier than the liquid sitting below. So it's again creating similar to the iron snow regime, but this time it's not the remelting crystals, but it's just coming from the crystallization process. It's again creating large scale fluid motions, which could induce a dynamo. And the major difference compared to the iron snow regime here is that you can drive this process as long as you haven't reached the eutectic temperature. As soon as you reach the eutectic temperature in your system, you, of course, crystallize everything similar to inner core growth, and then you don't have a dynamo. Also here, the heat sources, you have latent heat being released by freezing and gravitational energy being released due to the remixing of iron-rich liquid. And the temperatures look extremely similar to what we have for the iron snow regime. So let's go to some examples in our solar system. Where do we find those regimes, or where do we think we can find them? So first example is Ganymede, because I've been working on that during my PhD, you know. So to motivate things a bit, Ganymede is the only moon in our solar system that possesses a present day intrinsically generated magnetic field of quite substantial magnitude, like 7,190 nanoteslas. So I think this has been obtained only by 6 flybys, but we are going to have the JUICE mission who's going to put an orbiter at Ganymede, and we will have much, much better data in the 2030s. And there have been different, after this discovery, there have been different ways of explaining this magnetic field, because I think the community was quite astonished that such a small planetary body can create a present-day magnetic field, but it is likely generated in its metallic core. And as I said in the beginning, it's important to know what your melting temperature and core temperature look like. And we did this exercise for Ganymede. And you can see this in those two panels here for an assumed iron-rich liquid being on the iron-rich side of your eutectic and a sulfur-rich liquid. And you see the solid lines are your core temperature. This is assumed to be an adiabat here, and the dashed lines are the melting temperature for different sulfur concentrations. And you can see that for a variety of sulfur concentrations, you actually have top-down freezing because the two temperatures meet at the top of the core, which is indicated here by the relative radius 1. And the same is true for the sulfur-rich side. Yeah, when there is more sulfur in the system than the eutectic concentration. And the implications of that I have just shown you on the slides before. On the iron-rich side, we will have iron snow. On the sulfur-rich side, we will have a solid iron sulfide layer at the top of the core, floating above, so to say, a liquid core. What we did is we modeled the thermal evolution of Ganymede to find out when does the core freeze, and to find something out about the timing of the magnetic field and also its strength. So this is roughly a really rude sketch of the interior structure of Ganymede. We do have an ice-water layer at its outermost part. Beneath that is a rocky mantle, and the very interior is a metallic core with likely some light alloying elements. We don't know which, but we assumed in this study that it's iron and sulfur. And then, of course, we have both the extreme cases, a pure iron core or a pure iron sulfide core. And in between, we varied every concentration. We did not justify at this point whether all these concentrations are feasible. We just wanted to see what they entail in terms of magnetic field generation. And then this is the simple setup of the thermal evolution model. It's a 1D model. We do not treat the ice-water layer, which is reasonable because in the rocky mantle is the bottleneck to losing the heat from the core. Convection in a rocky mantle is so inefficient so that a lot of it determines how much heat is extracted from the core. And for the core, we modeled the iron snow and the iron sulfide. So these are the results in terms of magnetic field strength. On the left-hand side, you can see the iron snow regime. On the right-hand side, you can see the iron sulfur regime, and you see surface dipole field strength versus initial sulfur concentration. And then a dashed line indicates the observed field strength. So I do have to say this is not directly comparable because the observed field strength is actually taken at a height of 400 kilometers. So it's not the surface. So this should be taken with a grain of salt. But we can say that the magnetic field strength matches the observed field strength when it comes to order of magnitude. And we can also see that the FES layer models produce higher field strength. These, I have to say, are all successful models, meaning that these models produce magnetic fields at the present day. So these are values for present day magnetic fields. And the reason why the FES layer models produces higher field strengths is that usually cores, given that the mantle density and the crustal density and the density of the ice-water layer are the same, cores with much more sulfur are much bigger because you have to match your mean moment of inertia and your the overall mass. And larger cores means that your magnetic field is closer to the surface, meaning you have less geometrical decay if you want to have the value at the surface. The other thing we plotted is the age of the dynamo. So the age of how long has the magnetic field been around? And what you can see on the left-hand side is again iron snow models, and you see age of dynamo versus initial sulfur concentration, and age. So a value of 4,500 million years would mean that the magnetic field has been around during the entire evolution of Ganymede. Whereas a very low value means it's a fairly recent phenomenon. And you can see for iron snow that the magnetic fields are rather young. They are all below 1,000 million years, meaning it is a recent feature. If iron snow is operating in Ganymede's core, of course. If you look on the right-hand side for iron sulfide layer models, you can see that you can have young and old dynamos, and you can also see that there is dependence on the viscosity in the silicate mantle. And we see that for increasing sulfur concentrations, the dynamos can become much older. So you can have magnetic fields that have been around for much longer time. And if the sulfur concentration approaches the eutectic, then you see that the magnetic fields become fairly young as well. So what does that mean in terms of observables? That means that if we could, by some means, determine how old the magnetic field of Ganymede is, we would be able to distinguish between both regimes, given, of course, that we think that those regimes could operate in the core. And also what a dynamo in both of these systems require is that we don't have an inner core. And so even though these things are not measurable in the near future, they might. What about the Martian core? So for Mars, there have been different estimates about the age of like when has a magnetic field been around, when not. So the most recent thing by Anna Mittelholz, recent measurements have been that dynamo action has been present between 4.5 gigayears to 3.7 gigayears. And I think whether the dynamo could have been there much longer, we don't know yet. Maybe there will be other measurements in the future. So I think this value here might extend also into this direction. We just don't know yet. However, what we know is that we don't have a present-day magnetic field on Mars. We only see this ancient crustal magnetic field. And it is difficult with inner core growth to reconcile that we don't have a present-day magnetic field. There is the possibility that there is just not enough energy available to produce a magnetic field. But in general, it's hard to achieve that. So there has been this model by Chris and Ann from 2018 on iron snow in the Martian core. And I try to depict like the different cases we could envision. Case A means that the iron snow zone has is present in the entire core and is already forming an inner core by accumulating those solid iron crystals in the interior. And case B means that the iron snow zone, so the snow zone only started to grow recently. So it's fairly thin. So, and you can see the results of these two different scenarios. Scenario A from Chris's and Ann's paper shows a snow zone that covers the entire core after 3.5 gigayears after beginning of the evolution. And you can see that you can have dynamo action right at the beginning of the evolution, which is usually a thermally driven dynamo. And then you can have dynamo action as soon as the snow zone is large enough to actually overcome a stable thermal stratification that always is present in those small planetary bodies after some time. But this also means that this is not consistent with the observations because we don't see so far any measurements that give you any hint that there has been a magnetic field during this period of time. If you go to a thin present-day snow zone, which should be below, not thicker than 400 kilometers, which Chris and Ann state in the paper or find, you can see that you are marginally consistent with the observations. So the field should be around a little bit longer, but you can play with mental parameters like viscosity in order to get that. And it is somehow consistent with the current estimates for dynamo light time. So meaning a present-day snow zone on Mars is consistent with the observations we have so far. Question is, can we measure it? I do have to say, I cannot say at the moment, but maybe we have seismic measurements, but I'm not sure whether they are that sensitive, such as snow zone, probably not. So, but everything may be different on Mars. I just talked about an iron sulfur system, but we know from the InSight measurements that we have fairly low densities in the core, and they can only be reconciled with a lot of light elements in the core. That means we are very likely on the sulfur-rich side of the eutectic. So that would not entail an iron snow zone, because then it is not iron that is crystallizing, but it is iron sulfide. And you can see here in the plot by Terasaki and colleagues that you have the plausible range of core radii, which is here on the x-axis, and this gray area for Mars. And then with recent equations of state for the iron nickel sulfur system and the iron nickel silicon system, you can see that you have to have a lot of sulfur in your system. So you have to start with 30 weight%, and you can go up depending on what you assume your core radius is. You can go up to almost 35 weight%. if we look at the space diagram by Fay and colleagues in 2000, we see that we are on this iron, on the sulfur-rich side, and we would crystallize iron sulfide. And we can also see what the relevant temperatures are that we have to meet somewhere in the core. We don't know if at the bottom or at the top. We don't know yet. Nobody has done the exercise. And but if you meet these or intersect with your core temperature, these temperatures, these melting temperatures, you will crystallize iron. So it might be that the Martian core is entirely liquid today. We don't know. Or if it crystallizes with these sulfur concentrations, it would crystallize in this regime, or it would create upwards floating iron sulfide crystals, depending whether it's crystallizing at the top or at the bottom. Mercury's core. So there has been this paper by Mathieu and Attilio in 2015. And so what they did is they did different various present day states of Mercury's core for various parameters they had in equations of state. But I do have to say these are not the most up-to-date equations of state. And back then they saw that they could have a variety of scenarios. They could have scenarios where Mercury has a deep snow zone and a double snow zone. And you can see those in those two plots, temperature versus depth and density. And you can see wherever the temperature is equal to the core temperature, you would have a snow zone, meaning you have a snow zone at the top and the snow zone at the bottom above the inner core. And here you would have a deep snow zone. I tried to indicate that in those plots, but I just realized that it's fairly faint, those small points here. So it means we have a variety of complex freezing regimes. But again, everything might be different also for Mercury, because this all also heavily depends on what kind of concentration we have. And we are now, so the community has now again shifted to that the conditions on Mercury must have been fairly reducing, meaning that there is not a lot of sulfur in the system. Yeah, so there is likely a huge amount of silicon, but sulfur may contribute only with 2%. And this means, this is a plot by Tirio from EPSC, silicon versus sulfur for different core radii and different temperatures. And you can see that you have a large range in the low sulfur regime that is crystallizing bottom upwards. So it's not that sure that Mercury actually contains any snow zones. That really depends on the concentration of the core. And then there have been models by Yuri and Knibbe in 2018 that also included the evolution of a conductive stable layer at the top, which I talked to you about, that you can be thermally stable in parts of the core. And they investigated the iron silicon system, and they saw that you can produce a core dynamo, but I do have to say they assumed rather large values for the latent heat, which actually gave rise to those convective motions in the core. So, but I do think in terms of Mercury, it will be really important to investigate the simultaneous evolution of the stable layer together with the growth of an inner core. Tirio, for example, sees in his simulations, which is actually taking the code from Sam, Chris's postdoc, like former postdoc, who also did a great model on calculating the stable layer in those planetary bodies. And he sees that for the iron silicon case, which is this blue case here, which is contrary to what Urian sees, he sees that there is just no area left in the core where you can produce a magnetic field after a short period of time. And for Mercury, we know that we have a present-day magnetic field, so that cannot be. Okay, the lunar core. I will rush through the lunar core. So there's quite some, if you look at the paleomagnetic measurements for the lunar core, there are two astonishing things. The dynamo seems to have been around for quite some time. So long-lasting dynamo, and we do have an enormously high field epoch, and we cannot really explain that because the field has been larger than the present-day Earth magnetic field. There have been thermal evolution models on this problem, and they saw either that models provide a present-day dynamo, which is not consistent with observations because the moon does not produce a magnetic field, or the dynamo was fairly early, which is also inconsistent with observations because the dynamo has been around at least until probably 2 giga-years ago. We also did some calculations, a master student of mine who did a really large set of thermochemical evolutions in the core, and he studied the iron snow regime in the lunar core and also the classical inner core growth. And what we can definitely say for iron snow, that it does not play a role in the generation of the lunar dynamo. Because as you can see, the dynamo generating time in the iron snow regime is really, really short. It's only some million years, and this can definitely not explain the observation. But if you go to inner core growth, you can have a couple of successful models. These are the dark green ones and the dark red ones. And either they die because they have not sufficient energy to produce a dynamo, or they die because the simultaneous occurrence of iron snow. And if you have something like that, then you would probably kill your dynamo pretty fast, because you grow your snow zone and then there's just no area left in the core to produce any large-scale fluid motions. Last but not least, freezing planetesimal cores. There has been also quite some work on this topic by Neufeld and colleagues and by Aaron Scheinberg. And they proposed a scenario where you have, instead of loose crystals forming at the top of the core, you have dendrites, because the material actually energetically tries to stick to the already solid core-mantle boundary. And these dendrites will concentrically grow inwards, and they might become unstable at some point. So what Aaron Scheinberg did is he did not model this instability, he just did some estimates. And he investigated how efficient thermal convection could still be, given that you have those dendrites and the light alloying elements working against your thermal convection. And he sees that you can produce dynamos, which for a short amount of time, from like 4 million years, maybe even less. And the model by Neufeld investigated what it would look like if you have those dendrites and then you continuously delaminate those dendrites. And then you have like a chemical buoyancy, because you are taking this solid material and you're bringing it down into your core, and then you mix the remaining liquid. And you can see that you can have dynamos for quite some time, even until 20 million years, almost 20 million. So last but not least, I wanted to say something about what I think maybe the frontiers in core freezing will be in the near future. So I think it might be important to model multiple freezing zones. This is not that easy to do in a 1D model, so we have to think of innovative techniques. It will be important to simultaneously model the evolution of a thermal and stable chemical gradients, which is also challenging in a 1D model. And we probably need knowledge from experiments, from more sophisticated 2D, 3D models. 2D probably is sufficient. And then we should investigate non-equilibrium. There will be a talk by Andrew on non-equilibrium slurries. And we also have an ISI team together with Chris, which is probably not that progressed that fast, that much as Andrew is going to present. But so he's not presenting about the ISI team, but he's going to have more results. And then I think what is also really important is that we try to think of how could we compare our results to observations. So can we differentiate between the different scenarios? Because all of this is just paperwork if we cannot say anything about the real bodies out there. Yeah, so that's it from my side. Thank you so much for listening.
Okay, so we have time for questions. We will alternate between the audience and online. We can monitor the questions online. Any question, Tina?
Just quickly add, anybody online, if you'd like to pose your questions in the Q&A chat function, we'll read them out to the audience here.
Yep.
Yeah.
Sorry.
For the work you did looking at the duration of dynamo on Ganymede, I was wondering, how did you run like a full thermal evolution model of Ganymede to figure out how long dynamo would last, or like how did you determine the length of dynamo?
Yeah,
duration?
so we ran full thermal evolution models from what we assume to be the start of the thermal evolution, like 4,500 million years ago. This is, of course, also just an assumption. If Ganymede formed later, it would have started later. I think this is still also a matter of debate. And then we use scaling laws, from dynamo theory. We did energy estimates or power estimates, and we gained from the thermal evolution model, and then we could plug them into the scaling laws and estimate some strength. Yeah, thanks.
Okay, this may be a very embarrassing question,
Okay.
because my level of ignorance
maybe
has been exposed this morning. early on, when you were talking about Ganymede, you
Yeah.
had your two scenarios, and
Yeah.
one had a much stronger field than the other.
Yeah, yeah.
And that made me immediately think of concepts of Mars, because paleomag field has always been, much stronger.
If
than we
there's
expect
also
than the
iron
Earth.
sulfide, yeah.
So
yeah,
is that part of the picture potentially?
that's a good question. I think one would actually have to look into that into more detail, because as you saw, it really also depends on what exactly your setup is. So the thing is, like, it really depends on the size of your core. Yeah. So I think for the results I showed for Ganymede, this is mostly an effect that is due to the size of the core. Because what we did is that we did not assume the same core size for all concentrations, but we tried to consistently calculate what is the core size depending on your sulfur concentration. Meaning that we kept all other parameters constant, density in the mantle, density in the water ice crust, and the radius the overall radius. And then we calculated, depending on the sulfur concentration, the density in the core. And of course, the density for sulfur-rich liquids is much lower, and this will give you larger cores in your interior structure model to be consistent with the MOI and the overall mass. So I think this is mainly the effect you have here, that you saw that on Ganymede. And the question is, whether you could translate that to Mars directly. I think it really depends on the setup. What is the size of Mars core? And then we would definitely just have to calculate what would be the magnetic field strength. So maybe we cannot directly correlate. But from what I've seen for the inside measurements, I mean, the Martian core is quite large, larger than probably initially estimated. So I think right now it's 1,800 kilometers to 2,000 kilometers, something like that. 1,900. So it might be that you have strong field strength. But anyway, you would have the same field strength then also if you had classical inner core growth, but classical inner core growth you don't have. The question is, for the iron sulfide case on Mars, is that you should not produce a present-day magnetic field anyway. So we really would have to think of what that means in terms of the Martian evolution. I think it has not been discovered. It's just like or investigated. I hope I did not confuse you, or maybe we can talk in the break.
The level of complexity at least said that my question wasn't stupid, so I win.
No, it wasn't stupid. I think it's an open issue.
Perhaps one more question. Do we have any online? Maybe I'll ask one.
Okay.
The iron sulfur system, you are assuming that sulfur would partition completely in the liquid?
Mm-hmm. For those small planetary bodies, yeah. So
there's a high pressure.
It's not the case anymore. That's true. Yeah, if you go to Earth, for example, totally different picture. But I'm not sure for Mars. I do have to say, but I do have at the back of my head that it also doesn't play a huge role at 21 GPa or 19 GPa. One would need to consider. I would say for those small terrestrial planetary bodies, it's fine to not partition it, but you probably know better than you. Yeah.
Okay, thanks very much.
Thank you.
Thanks, Tina, again. The next talk speaker is Ludo Ugue, laboratory model for iron snow in planetary cores.
Everyone can hear me? Yes. So today I will talk about a laboratory model from iron snow in planetary core. So thank you, Tina, for having presenting the iron snow scenario, the iron snow regime. And so what I want to show you with my presentation is that the iron snow, the idea of the iron snow as presented by Tina, is a very bad, simple and naive scenario that I think we can put more detail on in terms of dynamics. So Tina showed that we can solve the thermal evolution in one day with some basic or more complex evolution models. But actually we need to know more about the dynamic the dynamic of this iron snow and how the crystals move and settle to or remelt into the core. So I like this figure from Tina 2015 paper, show is it the basic idea of the crystal, free crystal going from the top and remelting in the outer and deeper place, like and induce convection by the remelting of the releasing of the iron, pure iron liquid. So as Tina showed, top-10 crystallization can occur in small planets like Mars, Mercury, or even on smaller asteroids. So this kind of iron snow regime produces a compositionally driven convection due to the release of the pure iron liquid, and it's able to sustain a dynamo by the convection. Is this only in the convective region here? But actually, in the snow zone, you can have also some large-scale motion that may help to sustain a dynamo with a longer life. And what we know also about the iron snow is that the iron snow is quite similar to the F layer, what I think Andrew Walker would talk about in his talk. And there are both similar mechanisms of how the crystals can go and sink into this layer. And here is a picture of industrial casting. So this kind of crystallization of free crystals always coexist with a mesh zone, and the mesh zone is where you have a dendrite, solid dendrite attached on the surface. So, and here is a list of what we don't know about the iron snow. We don't know that if the free nucleation barrier is a valid assumption. That means that are we sure that the crystals can the crystal can nucleate from the bulk of the liquid core, and they are not attached at any surface or like the core-mantle boundary. We don't know the equilibrium state of the snow zone, if how large the departure of the equilibrium is. We don't know also the interaction between the crystallization, the stratification in the snow zone, and the convection. As I think the talk of Catherine and Quentin, they will talk about that more. We totally ignore the size and the distribution of size of the iron crystals. So Tina proposed in this paper that it may be on micrometers, but actually the size of the dendrite for the Earth's inner core was is more like a meters scale. And we don't know also the evolution of the stratification in this kind of snow. So if you have a stratification with crystals settling inside it, what is the interaction? Can we keep the stratification, or the stratification is destroyed by the motion, the fluid untrained by the crystals? So Jenny in his paper in 2020 shows that we can keep the stratification in the steady state, but we miss some element to know the origin of this stratification. So that raises a lot of questions. What is the dynamics of the iron snow, and what is at the scale and the time of the crystallization? What is is it the snow zone at the equilibrium or not? And how the snow regime contributes to the dynamo via large scale flow on the stratified layer and in the convection layer below the snow zone. So what I did is I built an experiment. So it's an upside down experiment of the snow zone. So you have in a planetary core, you have the crystals. It's the downward snow. So the crystals are crystallized near the top of the boundary, core-mantle boundary, and they are remelting when they reach outer place, outer region deep in the core. And what I did in my experiment, and I'm cooling from below, a pure water. So it's only pure water, and then cooling from the top, so we will crystallize pure ice. And to avoid that the ice will be attached at the surface, we are adding a salty layer at the bottom. So it's a green layer, so it mimics the mantle, but it's fluid. So it's produce a fluid interface between the solid layer and the pure water. And because the ice will be less dense than the water, when the ice crystal will grow, they will rise towards the top and we melt because the top boundary is warm, is above the liquid. So like that, we avoid the nucleation side because we don't want the ice crystal to be attached on the surface to mimic the snow. The ice crystal will be on in the form of platelets. That means they are almost 2D crystals. And so in this kind of experiment, you can have both crystallization, like a kind of snow zone, the settling towards the rising towards the top of the ice crystals, and the remelting of the snow zone that can produce some convective motion. So this is a video of my experiment. So the experiment is about 20 centimeter high, 30 centimeter width. And so here you have the pure water level in white. The salty water is in black in this picture. All these dots are just some bubble, but do not interact with the crystallization. And the video is speed up by a factor 100. So you can see that all these gray area are tiny crystals, and those are crystallizing and directly going up and remelting these. So we cannot see them because they are not anymore. And you can see that it produces some kind of wave or periodic. You have some burst of crystallization. All the crystals disappear and occur again. And you can see that there is some tiny crystals that are here and more large crystals at the beginning of the beginning of the burst of the crystallization. And later, you can see that the snow zone layer go a bit in thickness because the overall temperature is decreasing in the tank. You can see even really big crystals and with tiny crystals that we melt just above the liquidity that is around this size, this height. So what we can learn about that? So this is the temperature. So we can measure the temperature on the below. We cannot measure the temperature inside the tank because if you put a temperature probe inside, the crystallization will occur on this probe. So we can just measure the temperature at the bottom and at the top. So this is the red line. So the temperature in the bottom plate is around -15 degrees, and the top plate is around 10 or 8 degrees. Actually, there is no temperature set at the top. It's just only the flux of the outside room. So the first burst occur after 3 days of cooling, so nothing happened. Nothing happened here, and after 3 days of cooling, you have the first burst of crystallization that is here. And what I show at the bottom is the time. It's a temporal spatial diagram. So this is the time here in this direction, in this direction, it's the height of the experiment, and each gray patch here, it's a burst of crystallization. So you can see there is a burst, no crystallization, a burst, no crystallization, and you can see that all the crystals, the larger crystal can make up to the top once the overall tank is cool. Is cool from below, much quicker than the heat can enter from above. So we can calculate or estimate the supercooling that it's just between just above the salty layer, and we estimate that the supercooling at the first burst is about 20 degrees, minus 20 degrees. So we can also calculate the timing of the crystallization and the timing of the quiet period. So this is blue, it's the time of the crystallization, so the duration of each burst of crystallization. So it's about between 1,500 seconds, 500 seconds, and the cooling, the quiet period between each crystallization where the fluid is cool, it's about the same order of magnitude. So during the crystallization, so the crystallization time decreases with time, but because the larger crystals are removed much faster when at longer time from here. For example, the crystallization is quite a bit shorter than at the beginning, and the cooling, the quiet period, it's a combination of the diffusion you need to cool below the melting temperature to have some supercooling to produce some new crystals, and it's also in addition with the probability to have a nucleation event. It's not only about how much you can cool down below the melting temperature, but it's a question of can we have some nucleation event. Yes. So this is the evolution of one burst. So at the beginning, you have some crystallization from one side, and you have some collisional breathing. That means that the crystals are colliding to each other, produces tiny crystals that move this direction and producing a new crystal, even more crystallization. So you can see here that you can have some large crystals with some tiny, very tiny crystals of ice. So the larger crystal rise at about 2 millimeters per second, so quite slow. The larger crystals can even overshoot the liquidus because they are rising faster than melting rate. The smaller crystals are rising about 0.07 millimeters per second, and after about 1,000 seconds, you have the end of the burst. You have no more crystals. So how do we interpret this kind of burst of crystallization? So at the beginning, this is a sketch of the temperature just above the salty layer. So the temperature decrease. We have some degrees of supercooling, and from at one point you have a nucleation event. The temperature above rise at near the 0 degrees because you are forming ice. You are close to the equilibrium, and it's cooled down again. And the typical time scale of this period is about 1,000 seconds. So it's quite similar to what occurs in a natural environment where below ice shelf you can have some fossil ice explosion, or where you can have some super cool layer which will be convective in this kind. So this is a salt sea ice. You have some supercooling, and at one point you have a nucleation event, and you will grow a lot of crystals that will settle with it. They will rise and accumulate at just below the ice shelf. So this is a model that representing that, the temperature as function of the time. And when you have a nucleation event, the temperature rise close to the 0 degrees. And if you don't have nucleation event, the temperatures continue to decrease. But actually, the fuzzy ice explosion do not only depend how much supercooling you have, it also depends on the nucleation rate, and especially the secondary nucleation rate, which correspond to the collision and breaking the breaking of ice into tiny crystals. It depends also of the thickness. So here's a regime diagram. You can see that you can have fuzzy explosion here in this region, but if you are with less nuclei and less thick snow zone, you don't have any nucleation event and any fuzzy ice. So we also calculate the crystal size distribution. From above, we take image from above with a horizontal line laser sheet just above the snow zone, and we are calculating the area that's of each crystal crossing this snow zone. So we can detect the smallest crystal we can detect is about 0.3 millimeter radius, and we varying the threshold, which means how we can detect the crystals from the image, but actually varying the threshold does not change the overall shape of the distribution. So in this image, all the white spots are the crystals that are crossing this laser plane. So we are doing that for 8 bursts of crystallization over 6 hours. And this is the distribution. This is the PDF of the size of the crystals. So this is the radius, this is the probability density function. And you can see that it's decreased as a power law, like that. And this power law is nice because it's kind of having a fractal dimensions, this d parameter. And if this d parameter is less than 2, the total area is dominated by the largest crystal. So you do not need to know the size of the smallest crystal. You only just need to know the largest one. And actually, in our case, the fractal dimension is around 1.8. So from that, we can calculate the total area of each size of crystals here. And because the dimension fractal is less than 2, the larger crystal dominates the total area, even there is less of them. So there are few large crystals, but because they are large and the fractal dimension is less than 2, they dominate the total area. From that, we can also estimate the mass flux of these crystals. So to calculate the mass flux, we need to know the distribution of area for each size of crystals. We need to know the velocity and the density of them. So the velocity we can calculate from here, like that, depending on the size of the crystals, for sure. And you can see that the total mass flux in this burst of crystallization is dominated by the larger one. So we need to take into account in this iron snow or snow event that there is large crystals that can drive, that can modify the stratification in the snow zone. Thank you very much. If you have questions.
Time for one quick question.
Thank you, Ludo. I have a quick question regarding this quiet periods. Because I kind of see like 2 kind of time scales, one time scale associated to the cooling of the system and one time scale associated to the rising of these crystals.
Yeah.
And so it looks like you need to remove these crystals to be able to cool again.
Yes.
And so for planetary cores, what kind of what would be the relative time scale of this? Can we have like regime where crystal rise so slowly?
Actually, yes, the two time scale here are quite similar in my experiment, but I think it won't be the case in the planetary core. Because when we are thinking about crystal thinking in planetary core, for example, I did a calculation for 100 kilometers thick. It's not only if you calculate the times it makes having crystal taken from the top to the bottom of the nozzle, this could be a day, week. Even they are small.
Okay, thank you. We have to move on to the next talk. Next one up is Andrew Walker. He's going to talk about a non-equilibrium model of slurries in planetary core.
Okay, so I'm Andrew Walker. This is a result of a international collaboration seed corn project to try and enhance international collaboration that we won in January 2020, which was a lot of fun. So yeah, this talk is really looking at if we put non-equilibrium processes into a model of a slurry, in particular a model of the F layer, so the base of the Earth's outer core. What happens? Can we find out more than we could without the non-equilibrium processes? And how would a non-equilibrium model be different to an equilibrium model? And sort of just what is the simplest way we can go about doing this? Right. So we've seen a nice talk by Tina earlier, that these slurry zones, so zones where you have a small volume fraction solid within a bulk liquid in a metallic planetary core, have been invoked for a wide range of bodies, Ganymede, Mercury, Mars, etc., in a range of different ways. So you can have the slurry layer, the snow layer in different places. What I'm going to focus on is the case where you form the small crystals of iron deep in the core above a solid inner core, which corresponds to the Earth, or might correspond to the Earth. In the Earth, there's this thing called the F layer, say 200 kilometers thick layer that's seismologically different to the bulk outer core. And one explanation for this is that it's a slurry zone. We've got the iron that forms, the solid iron that forms and grows the inner core, actually crystallizes in the liquid and settles out of that layer. Okay, so let's start with a phase diagram and a depth temperature plot. So if we look over on the left-hand side, I've marked a point on this diagram. The red line is supposed to indicate the temperature. The black dotted line is the liquidus, and the system I'm going to think about is iron-oxygen alloy, the liquid. The oxygen stays in the liquid. And the reason I've chosen that is because there's a convenient thermodynamic model, and you'll see we need a full thermodynamic model for these calculations. So the idea is that we're in a regime where we are below the liquidus, but above the eutectic temperature, which means in a phase diagram on the right hand side, we just look at the black lines, which are the calculated phase diagram. We're somewhere in this two-phase region where we have iron oxygen liquid in equilibrium with iron solid. And as many of you probably learned in first year geology, you can if you know the total composition and the temperature and in fact the pressure and have the phase diagram, you know the liquid, this is liquidus, solid is pure iron, and you can work out the volume fraction of the solid and liquid. And that's assuming equilibrium and conservation of oxygen. And for an equilibrium model of these layers, actually all you really need is the liquidus, some parameterization of the liquidus, and you can go ahead and do the whole calculation. It's not as easy as that, I'm sure, but the input is the liquidus. What I'm going to do is think about lifting this assumption of equilibrium, which means my liquid composition no longer needs to be on the liquidus. And what that means is that you are, or we are incorporating kinetically controlled processes. So things that slow down growth, things that stop the formation of crystals like nucleation, and things that give us a time scale, like how long do these crystals hang around in this layer before they settle out. We're putting time in. That's why we can be in non-equilibrium, why we're only approaching equilibrium or in equilibrium. But it also tells us what we get out of these calculations, which is anything that depends on time. So we can get out how long does a crystal live in the layer, how fast does it fall, how big it is. Right? In a purely equilibrium calculation, you sort of have to put those in afterwards as in some way. It's quite hard to have that come out of the calculation. And I've highlighted now the thermodynamic model, because to do this, we need to know the free energy difference between a liquid with some amount of oxygen in it and the solid. We can't just, so we need a full thermodynamic model. We can't just get away with the liquidus. So there's got to be some underlying thermodynamics. And that's actually what's going to drive all the processes. This, you'll see it in equations as delta mu, the difference in the chemical potential between the ion in the liquid alloy and the ion in the solid. Okay, so how are we going to do this? How did at some point in April, May 2020, just decide this might be a sensible thing to do? We're going to, first of all, think about a single crystal, the lifetime of a single crystal in this system. So it is at some point it's going to nucleate. I'll deal with nucleation later. I'm going to assume it's homogeneous nucleation. We can live with that. There's problems with nucleation, but it's a nucleation event. In this pure liquid, which is super cooled, so it's in the two-phase region. The crystal then wants to grow. It also wants to sink. And we're going to set up equations that describe the sinking of the crystal and the growth of the crystal. And part of that growth is got to expel the light element, oxygen, from itself as it grows, because oxygen doesn't enter the solid. That's for one crystal. And then we, in sort of a second stage, consider the density of crystals you might get on average from this process, and handle the latent heat and in principle the oxygen production from the layer in a way that that matches that to a conductive cooling of the layer. So we're saying implicitly that the layer itself, the liquid in the layer, doesn't move as a simplest assumption, and the heat and the light elements got to escape via conduction and be matched at the upper boundary. So the cooling of the bulk of the outer core is driving cooling of the layer. And this gives us the things that you would have to put in to a fully dynamic model, right? You can't, we would somehow have to parameterize the solid growth and solid sinking in a fully dynamic model to do that, to build a fully dynamic model. I think that might be a poster that, Frederick's got a poster that shows quite how hideous that might be. Okay, so falling crystals. One of the things we need to know is how fast the crystals fall, and that's basically Stokes' flow, except it's not, because we quite rapidly reach a regime where there's additional turbulence around the crystal that that increases the drag coefficient. So we have to use like an empirical solution for falling velocity. It's an empirical drag coefficient. That requires a self-consistent solution for the Reynolds number and the falling velocity, because they're mutually dependent, or they become mutually dependent. That's all okay. This process also, or the falling crystal also has a boundary layer around it. And as you'll see, we're going to need to know the thickness of this boundary layer, which we take from simulations of single falling crystals actually designed for oceanography. But they give us a scaling law. Actually, the scaling law gives us thickness of the boundary layer around the equator of the spherical falling particle. Spherical particles here, no, not platelets. But we assume that the whole thing is spherical. As I say, we're exploring the physics, not trying to get exact answers. Okay, so then we need to say something about crystal growth. And the first thing to say is that crystal growth of pure metals, at least what we know about them, we don't know very much at all in high pressure conditions, is fast. Part of that is because metals have quite a high nucleation barrier. So they're typically undercooled, so they typically grow very quickly. But another part is the liquid metal structure and solid metal structure, pretty similar, only a little change. So you can have this high growth velocity. And that depends on your undercooling. It depends on the undercooling because it depends on the difference in free energy between the solid and the liquid. Now, the complication is that we have this iron alloy. So we need to worry about the oxygen that, in a sense, is being produced kind of on the outer boundary of the growing crystal. And it's that concentration of oxygen on the outer boundary that sets the chemical potential, sets the growth velocity. But we also have to move the oxygen away through our boundary layer into the bulk oxygen content of the liquid. And that means we have this coupling between diffusion in the liquid, oxygen diffusion in this thin layer, boundary layer in the liquid, and growth rate. So that sets us up a second problem we have to solve consistently. And of course, they're interrelated, they're linked by how fast the crystal's falling, because that sets the boundary layer thickness. So what we end up with for a single falling crystal is a pair of coupled ordinary differential equations which both have this self-consistent optimization in them. So the first thing we looked at was, well, let's just imagine a crystal nucleates. I think we said 10 nanometers initial radius. The initial size doesn't actually matter very much. 200 kilometers above the inner core boundary. How long does it take to fall? How big does it get? Varying some parameters, which we've got some uncertainty on, and just get an idea of how big these things could get if you take the model at face value. So the two probably most important parameters are the viscosity of the liquid, because that's going to determine how fast the crystal falls, and how thick the boundary layer is, and the oxygen diffusivity, because that's what's putting the brakes on crystal growth if we ignore nucleation. And as we change viscosity on these plots by following one of these lines, actually not very much happens to the size of the crystal. The size of these dots are the size of the crystal as it hits the inner core boundary. And that's because the growth rate and the falling velocity scale in very similar ways with viscosity. As you change oxygen diffusivity, the particles, as oxygen diffusivity increases, particles can get a lot bigger because they grow faster. But we end up with falling times between days and a year. We end up with crystals between sort of millimeters and meters on the upper end. Meters is probably the extreme end of what is a reasonable parameter to possibly take, but centimeter-sized crystals seems about what we would expect for this single crystal falling through a layer. So the next part is really putting in the nucleation, putting in the density of crystals, and thinking about what the layer looks like overall. So really what we do is think of a stack of volume elements above the inner core boundary through the layer. And each element, we're going to think about the waiting time for a nucleation event to happen. And then that crystal is going to start falling. And then some waiting time later, another particle is going to form and start falling. So from the particles in that single volume element, you get a vertical spacing. One's falling behind another, and the distance between them depends on their velocity with time. And we can do that calculation for each volume element stuck on top of each other. And that gives us, we can then add the number density of these particles together. That gives us a total number density of radius. That's essentially what we need. So each volume element, we only actually need to do a single particle falling calculation. And then we do this, it's an integration of depth to get the number density of particles and the size distribution of these particles as they fall. And we're assuming that this has reached some sort of steady state. Hugo's talk was interesting. It looks like steady state isn't steady. It's got this, this generation of lots of more crystals once you have a nucleation event, but not in this calculation at all. So we need to have some form of time delay between crystals. We appeal to classical nucleation theory to do this. Of course, anyone who's been following the core nucleation literature will be aware that this is a problem. We shouldn't have an inner core, or if we do, it should be bigger than it is. And if that's the inner core, then the problem with the slurry is that that's one nucleation event over the lifetime of the Earth. We're never going to have hundreds and millions of nucleation events. But we can use the physics. So what I've done is use the physics of classical nucleation theory, but put in heterogeneous nucleation on the basis that maybe there's some solid dust from somewhere floating around in the outer core. We're still trying to work out what that might be, but maybe from planetary formation. But got to have something if we're going to have a solid model at all, and that seems the easiest, or the thing that seems least objectionable. Okay, so what we get out of this calculation, we then generate a load of particles, let them fall, dump a load of heat and oxygen into the layer, solve a conduction equation, balance the production of solid and loss of heat, and get out the temperature profile. And I'm going to finish with this plot. So talk you through it though. The black dotted line is the equilibrium liquidus. Okay, and we're tying everything to have the liquidus cross an adiabat at 200 kilometers above the inner core boundary. And then each set of lines with circles on is a calculation. Temperature comes out of one of these calculations. And what I'm doing is I'm adjusting my parameters in classical nucleation theory to change from something that's like equilibrium to something that's got very, very low nucleation rates, essentially no crystals. And what we have is, as we go from no crystals for this system, we have no heat production, relatively cooled, no inner core growth. We have isothermal layer. As we gradually turn on nucleation, or make the kinetics go faster, we move towards what we would expect for the equilibrium case, which is the temperature we calculate follows, more or less with some wobbles, follows something like the liquid, which is the equilibrium result. So it seems that yeah, really. Yeah, questions?
Thank you for a nice talk, Andrew. So the oxygen diffusivity essentially is controlling the thickness of this layer of expelled oxygen around your your crystals as they're growing. And so that then changes the local equilibrium at the surface. But you've said that most of your crystals are larger than the Stokesian size. So you've got a lot of turbulence around them. So are you including turbulent mixing within that oxygen layer?
So no, we're not. So the thickness of the layer is actually set by the falling velocity of the crystal, and the diffusivity is setting the timescale to get through that layer. These turbulent mixing, what it does is it gives you a sort of a boundary layer around the front of the falling crystal, and then turbulent tail plume out the back, and we're not doing that at all. What we do is say, there's a scaling for the average thickness of the momentum boundary layer, and we're looking at diffusion through that momentum boundary layer, which then, I think the idea would be that it gets to the edge and then gets turbulently entrained, or that deals with the mixing of the layer. But yeah, these things to do properly, it's super, the dynamics is like super complicated.
So I think we need to move on to the next talk. The next talk is from Catherine Dodds.
Hi, can you hear me?
We can, yes.
Right.
Share your screen, Catherine.
Yeah.
So inwards core crystallization, insights from analog experiments.
Hi, so thanks for having me to speak today. I'm going to be talking about some analog experiments we've done looking specifically at the possible modes of inward core crystallization in asteroids and the sort of possible ways that a dynamo could be generated in these small planetary bodies. So the sort of main motivation for all of this work has been the meteorite paleomagnetic record that we've now got, which has shown that the cores of the meteorite parent bodies, which are generally sort of thought to be these sort of 10 to hundreds of kilometer size radius planetesimals, were actually capable of generating a dynamo field during core crystallization in the sort of first couple 100 million years after the start of the solar system. However, given their small size, it's likely these cores crystallized inwardly, so in a very different way to Earth's core currently is, and Tina gave a really nice introduction about the different ways that this can proceed. But with the asteroids, these really small planetary bodies, there's not been quite as much attention on the modes of core crystallization in these bodies compared to sort of the bigger planetary bodies like Ganymede. We do sort of have two possible mechanisms that have been proposed for the asteroids. So the first one here on the left is this melting of iron snow model developed by Tina Rukriman for Ganymede, more specifically. And then on the right, we've got this delamination model, which has been developed by Neufeld et al. In 2018 and also Scheinberg et al. In 2015. In this talk, I'm mainly going to look at this iron snow model and how we might apply this to asteroid-sized bodies. And that's because this model has been developed for a planetary body that has got a decent-sized mantle. So actually the core cooling rate's quite slow. These lamination models with these sort of delaminating dendrites have been specifically developed for the 4A meteorite parent body, which is believed to have been mantle stripped. So you can form an iron crust and a thick sort of mushy layer at the top of the core, which can then delaminate, and then these falling dendrites can sort of stir up that liquid. Whether this is actually possible in a sort of more typical mantled asteroid is more uncertain. So I'm mainly going to concentrate on looking at this iron snow model. So here's just a brief overview again of the iron snow model. We end up with, we pull through the CMB, we form this stable snow zone in which crystals form, and they fall through the snow zone into the interior, which is now hotter than the liquidus temperature, which is given by the orange here, remelt, and it's the remelting of these crystals that actually drives compositional convection and a dynamo field in this model. So one of the key assumptions in this as well is that there's thermodynamic equilibrium in the snow zone. And this is something we can look at with our experiments as well. However, when we start to think about applying this to an asteroid-sized body, we find that we might not get this remelting. And this is due to the really small pressures of these asteroid cores. So we're generally looking at pressures of less than 1 GPa. And then when you calculate the adiabatic difference between your C and B and the center, we're looking at sort of less than 5 Kelvin. So if we do get remelting, it might not be happening right at the top of these cores. And if there's any sort of significant degree of supercooling, which we might be requiring, we might not get any remelting at all. So down here is sort of like a little schematic of what might be happening in an asteroid instead. So we might still have a snow zone, but in this case, because of these low pressures, the snow zone might not actually, so base of snow zone might not be hotter than the melting temperature of the crystals. So instead, these crystals will just fall out of the snow zone and passively into the core. So that's sort of what the iron snow model would assume, that these crystals aren't actually adding anything to the flows necessarily. But what we wanted to look at is there actually any way that these solids that are falling can generate any kind of flow? And to do this, we used some analog experiments in the fluids lab. So similar to Ludo's, but without any remelting, to answer these two key questions. Firstly, can these falling crystals provide any additional power to drive a dynamo, or do we require remelting? And then secondly, just trying to look at this assumption of thermodynamic equilibrium for using that in modeling sort of iron snow-like regimes. We'll also have a look at whether the iron snow model has got, is there any physics in there that maybe the iron snow model is not capturing? So this here is a sketch of our experimental setup. In this case, we've got a tank that's about 30 centimeters tall and 10 centimeters wide. And here we're going to cool from the top, not from the bottom. And we're going to cool through this buoyant fluid layer at the top. This is actually propanol up here, and that was added to prevent the nucleation of crystals from the cold plate, so we could actually form free crystals in the tank. And the liquid we were crystallizing was this supereutectic solution of ammonium chloride. And when this crystallizes, it's going to form dense ammonium chloride solids and expel water-rich liquid. This then here is our tank setup with sort of the initial liquidus and temperature profiles in the tank on the right. So the liquidus temperature is here in the green. So this propanol layer at the top is never going to freeze. It's got a really low freezing point. Whereas actually what's nice about ammonium chloride is we can get it to freeze at about a temperature, at room temperature. We're then cooling through the top, so we get this conductive profile through the buoyant layer. And then this small boundary layer at the top in which the temperature is now below the liquidus temperature, so we can form crystals at the top of this tank and then sort of see what happens. So this is a picture of our setup. We've got cold plate at the top here. This dark sort of black layer is that propanol layer, which we've dyed really dark blue. We've got 2 plane lasers on either side, and this illuminates a plane within the fluid and picks out any crystal particles that are in there. We can take videos of any convection and flow that then forms, and use software to actually look at the velocity field that we see in there. We can also measure the temperature at different depths using a thermocouple. So that's what we've got one in here. We were able to do this without too much crystallization on the thermocouple, but that was a bit of a problem. And finally, we can also, there's a hole in the top of the tank here, so we can go in with a syringe, we can extract some of the liquid, this convecting liquid down here, take it out, and using a refractometer, actually look at its composition, so we can get the thermochemical evolution of this setup, as well as being able to sort of look at the sort of power of any convection in there. So in terms of results, the sort of first broad thing we found was that we had 2 styles of crystallization, and we didn't really find any reason for whether it was in the snow regime, which is what we were looking for. So here you can see sort of lots of small particles in this tank on the left, and they're sort of entrained in the flow, and then we sort of grow a cumulative part at the bottom. And then our other regime was this dendritic regime, which these two had identical setups. They've both got a thermocouple in, but here, this one on the right, the crystallization's been dominated by growing sort of large, sort of centimeter-sized dendrites off the sidewalls. So we've got these 2 different regimes, and we're not entirely sure what controlled which one, but we could force the snowing regime. For the rest of the results, I'm going to talk just about the snowing regime, because this is the one we were most interested in, but this is just here to be aware that this was sort of quite a common occurrence just to form dendrites. So what we've got here is a film of one of these experiments starting to crystallize. In this case, the cold plate's at a temperature of -15, and it's sort of off a field of view here. We're looking at the tops of 7 centimeters of this tank. This is false color. So crystals in this are going to show up as sort of orange, white specks as they're sort of reflecting the light. This is also in real time. So it's not sped up or anything. So what we start to see is the formation of crystals just directly below the buoyant layer. And you get sort of bursts of crystallization that then grow and fall off in these dense plumes. So we're not seeing here just a passive settling out of these crystals. They're actually being entrained in the fluid, affecting its bulk density, and driving convection. As you can see, so yeah, they go down and some of it gets entrained back up, and then at the bottom of the tank we start to see some of them settling out. But they're mainly forming in this sort of very thin layer at the top of the tank. We can take this video and we can look at the sort of PDF of the speeds in there. And what we find for this one, where we've got -15, we get this sort of bimodal distribution, where this faster peak that's about sort of 2-3 millimeters per second is representing the sort of fast upwellings and downwellings, whereas this sort of slower peak down here is sort of less than millimeters per second. This is generally associated with like the middle of the eddies, or sort of around the edges of the tank where you've got some kind of shear slowing the flow. So we're getting peak speeds at around sort of 2 to 3 millimeters per second in this case. We then repeated this experiment, so we did this repeated this experiment and changed the fluid composition slightly so it wouldn't crystallize. So we could look at, for the same thermal forcing, what kind of convective speeds are we getting out when there's no crystallization. And this is the PDF now in blue of the thermal convection alone. So again, we're seeing this sort of same bimodal shape, but in this case, the sort of dominant peak here, which is representative of the flow, is centered around so about 1 millimeter per second. So the crystals, by sort of being entrained in the fluid, increasing the bulk density of that fluid, can actually generate faster flows. We repeated this for a range of velocities, and we got this out. So we've got driving temperature difference on the x-axis here, speed on the y-axis, and then the red's the crystallizing and the blue are the thermal speeds. The ones that are most representative of the flow are these top ones, and we find that for most of them, with the exception of this one here, which had a -10 at the top, we are seeing an increase with the crystallizing. The crystals are providing extra convective power. We can also look at the thermochemical evolution of the tank. So this here is showing the bulk liquid evolution, and so we start up on these right-hand corners here, and over time, so it's about 8 hours, they evolved to more water-rich compositions, and we find that this is the same for the snowing tanks, which are the red and the orange, as well as the dendrites. And the bulk liquid, we believe, becomes more water-rich with time because of the crystals actually entraining that water-rich liquid at the top, not expelling it and forming a snow zone. And then, so they pull the water-rich liquid down and expel it at depth. We also require a few degrees of undercooling to force crystallization, but that's mainly for kinetics. Just we need to get we need to get some nucleation sites before we can start to see crystals forming. And finally, there was no real sort of thermochemical evolution difference between the snow and the dendrites. So in terms of our key observations from these tank experiments, the first one was that the addition of the crystals to the fluid during crystallization can drive fast convective speeds in thermal convection alone, which was unexpected. We don't see a stable snow zone developing. Instead, we see the bulk liquid becoming more water rich as the crystals pull the liquid down with them. We do require some supercooling, and also we do find that actually forming these crystals away from the solid substrate is very difficult. When we're then thinking about applying this to a planetary model, we're not going to talk about this one for the planetary model, and we're also going to not worry about the supercooling. Instead, we're going to think about an asteroid in which asteroid model looks something like this. So this is kind of our possible model for core solidification. We're going to form iron crystals in some sort of boundary layer at the top of the core. They're going to increase the density of that fluid. These dense crystal-rich plumes are then going to delaminate off that boundary layer and stir up the interior. And then finally, we might be able to grow some kind of inner core by the settling out of these iron crystals. Finally, to quantify whether this is able to generate a dynamo field or not in these asteroids, we used this model. We varied the sulfur content of here, and we varied the heat flux out of there to work out the sort of predicted magnetic Reynolds number for the core. So that's telling us whether we can have a dynamo or not, and it's the product of the speed of the convection, which is going to be controlled by your CMB heat flux, the length scale of the convection, so how big's your core, divided by the magnetic diffusivity. So this here is a regime map of that. So on the x-axis, we've got CMB heat flux. So generally for asteroids during core crystallization, we're looking at something about 10 milliwatts per meter squared, so around about here. On the y-axis, we've got core radius. If it's grey, it doesn't generate a dynamo. The white contours here are different values of supercritical magnetic Reynolds numbers. So generally thinking between 10 and 30. So for these bodies, we can probably generate core dynamos during core crystallization if your core is less than sort of about 100, more than about sort of 70 to 100 kilometers. So this mechanism does seem to be able to provide the power required to generate a dynamo without remelting, which is nice. And then finally, it might be grain size dependent, because if you've got really big grains, so sort of meter size, even millimeter size, they're not going to be entrained, they're going to fall out. So we might actually require sort of sub-millimeter size grains to get this mechanism. And then just to conclude, we have identified this sort of possible new mode of inward core crystallization. However, this mechanism might depend on things such as your crystal size and also potentially your core structure. Thanks for listening, and I can take questions if there's time.
Any questions?
Catherine, thank you. That's a really great talk. I was wondering if you have any idea of what the solid fraction is in these regions that form downwellings, because it seems like they become really solid dominated. It seems like quite an important insight for the dynamics of the system if we're modeling it.
Yeah, so in these ones, it was quite hard to actually measure off the video themselves because the crystals act as scatterers. The solid fraction in these were in the experiments themselves, because we're quite high heat fluxes, were about sort of less than 1%. It was about sort of 0.2%. So it is quite a high solid fraction. When we've then scaled that to like a planetary core, it's much lower. It's like sort of 10 to the -4, 10 to the -5. But we were finding that with like basically the extra, because you end up with like a parcel of fluid that's got this tiny crystal fraction in it, but because that crystal fraction's got this really high solid density, it was still enough to generate the required buoyancy to drive convection. So yeah, it's pretty high in the experiments, but hopefully when you scale down to planetary, it's still high enough to generate convection.
Yeah, it's very interesting. Thank you.
Thanks.
Okay, thank you. So move on to the next speaker now.
Hi, everyone. Can you hear me?
Quentin Crea.
We can, yes.
Yes, okay, great. Thanks.
Compositional convection from to talk about compositional convection from iron snow, laboratory modeling with dissolving sugar.
That's it. Thank you very much. So thank you very much for having me. So I'm Quentin Crea. I'm presenting from France, where I am doing my PhD. I'm beginning my third year of PhD under the direction of Benjamin Favier and Michael Lebars. And I'm presenting experiments with sugar falling in water to model compositional convection from iron snow. And so now there has been a great introduction before me by the different presenters, but I'm going to just quickly remind what I need to introduce my experiments. So consider a planet. We're going to look at what's happening in the core, and suppose that the liquidus is steeper than the core temperature. In this case, solidification starts at the core-mantle boundary. And if you suppose that the core is made typically of iron and sulfur, as Tina said, and if you consider that the composition is on the iron-rich side of the eutectic, then the crystals are made of pure iron. They are denser than the fluid, and therefore they fall because of gravity. You have a snow zone developing. When they reach too large temperatures, they remelt. You now have an accumulation of molten snow, which is denser than the fluid underneath. It is not stable, and this leads to compositional convection. This is what I want to focus on. And to build a laboratory analog, what I need is a two-phase flow with an interaction between a fluid and grains that is reactive with a phase change, buoyancy-driven, and possibly turbulent. And so dissolution enables me to have all this together. And also there is a clear analogy between dissolution and melting, which I am illustrating now. If you take a solid in a very hot liquid, you have a receding front, as you can see, and only temperature gradients in the liquid. And now if you consider a solid which is dissolving, you also have a receding front here, and you can see only gradients of concentration of sugar in water. So in the first case, conservation of energy tells you that the velocity of the front is determined by the temperature at interface minus temperature at infinity. And in the second case, conservation of mass tells you the same thing, but instead of temperature, you've got concentration. And in both cases, K is a coefficient, it's a velocity telling you how fast you renew the boundary layer for melting or dissolution to keep going slower or faster. So a clear analogy, and because it's simpler for me in experiments, I'm doing dissolution. Anyway, in both cases, the phase change happens in a finite amount of time. That means that in a planet, you wouldn't have a snow zone on top of a convective zone, but you would have an intermediate mixing layer or melting or dissolution layer, where snowflakes have started melting, but they haven't finished. And we're about to see that it's important to take into account, because although you can have a uniform and steady flux of grains nourishing the mixing layer, you may not have a uniform and steady flux of buoyant fluid nourishing compositional convection. So let's have a look. What I do in experiments is I can automatically sieve grains of sugar above water. They fall in a green laser sheet, and as they reflect and refract the light, you can visualize the grains of sugar through a green filter. The first thing you can vary in experiments is the mass rate, which is proportional to the energy input. So a clear but paramount conclusion to keep in mind is that the larger the mass rate, the larger the energy input, the more intense the flow. The transient is going to be shorter, you will have larger velocities and a flow which is more turbulent. So for a given value of the mass rate, you can expect different types of flows. But actually, it's also going to be altered by the second parameter, which is the size of grains, which is what we're going to pay most attention to today. And we're going to be quantitative in a narrow region because this is ongoing work, but we'll be able to visualize the flow in a wider parameter space. So let's begin. What you can do is you can fix the mass rate, pick two different sizes of grains and observe what happens. So this is the mass rate I pick. And as you can see, in both cases, you reach a permanent regime. But when you have small grains, you have a shallow dissolution layer, which you can visualize. Whereas here with large grains, you visualize a deep dissolution layer. So to fix the idea, what you can do is in the permanent regime, you can take an average photograph. So again, I fix the mass rate, increase the size of particles rightward, and you can see that the larger the grains, the deeper the dissolution layer. This is completely expected. If you have a small grains, it falls with a low settling velocity and it has a large dissolution rate, which you can compute analytically. And at the same time, when you have a large particles, it has a larger settling velocity, but a lower dissolution rate. So during a given amount of time, small grains quickly disappear close to the free surface, whereas large grains travel long distances before disappearing. And if you want to be quantitative, what you can do is compute the typical depth where you see snowflakes, grains of sugar. So this is the centroid of the dissolution layer. This is what you can see in ordinate as a function of the mass rate of grains of sugar and as a function of their size. And please focus on the effect of size from small in blue to big in red. What you can see is that from blue to red, we have larger particles and therefore a deeper mixing layer. So that means that the grains of sugar are distributed in a very different volume here and there. So you can expect that the flow is going to be different. To see it and prove it, what you can do is add passive tracers, very small orange particles whose density is close to that of water, which play really no part in the dynamics, but their only action is that they're going to show you the motions of the fluid. And so it reveals the fluid motions underneath the dissolution layer. And then to be quantitative, by basically doing constellation tracking, you can do particle image velocimetry and compute the velocity field everywhere. So to be quantitative, what we can do is look at space-time diagrams. You've got depth in ordinate from the top of the tank to the bottom in time, and you're looking at the velocity magnitude in the fluid. So initially it's dark blue because there are no fluid motions in the tank, but at some point motions appear and they propagate downward in the tank until you reach a permanent regime. Again, I'm not interested in the effect of the size of grains for that slide, so this is fixed, and I'm just going to increase the mass rate rightward, okay? Please focus on the white and dark dotted line. This corresponds to the bottom of the dissolution layer. This is the deepest position where I can find a grain of sugar. So when you have a low mass rate, it means you have a slow flow, and so you have a shallow dissolution layer. And it turns out that the more vigorous the flow, the deeper the dissolution layer. And again, this is an effect of the velocity of the fluid. So to prove it, what you can do is you can compute the maximum depth of the dissolution layer from your experiments. These are measurements. Then you can compare it to the theoretical maximum value reached by a grain, which you can compute if you neglect fluid motions. So ZF is my measurement of the depth of the dissolution layer, and the theoretical maximum depth is in the absence of fluid motions. If fluid motions had no impact, you would have all the data points on the line which is in white here at 1. Turns out that motions always have an impact, and the larger the mass rate, the longer, the deeper the dissolution layer. So that means that the mixing layer is further stretched by more intense flows, which is intuitive. It's the fact that the grains of sugar are advected by the flow. It's like a river carrying sediments, and if it has a larger velocity, they're going to travel longer distances. So in the planet, it means that this intermediate layer is going to be deeper if you have larger grains or a faster flow. And what I want to insist on also is that in the movies you looked at just before, is that you could see the grains falling, and this is what created the motions by drag. Okay, but that was only half of the story, because as many people said before me, you also have, in my experiment, dissolution. You have a phase change that imparts buoyancy to the fluid. And that's the other half of the story, which is going to nourish the compositional convection. So to visualize it, I need another type of sugar, which I cook. So I cook fluorescent sugar by melting sugar in a frying pan. I can add rhodamine inside. So I get pink sugar. I let it dry, blend it to get different sizes of grains, which can be sieved, so that I can make a clear difference between the largest grains and the smallest ones. Pick the size you're interested in and sieve it above water. Again, you can see the grains falling. This is not new. We saw that before. But now, importantly, because you have colored molecules inside the sugar, throughout the entire process of dissolution, you have colored molecules which are released in the fluid. So you can see the sugary water which is left behind. So now in the laser sheet, when you can see orange fluid, this is negatively buoyant sugary water. And with one camera, we're going to visualize at the same time the grains and the fluid buoyancy. So when you start sieving, initially, the only thing you see is grains falling. But at some point, you can see a wavelength appearing for a Rayleigh-Taylor-like instability, which gets more and more nonlinear. And you've got coalescence of the different structures. A macroscopic motion appears that strangles the dissolution layer and creates that neck to form just one big lazy plume. And as you can see, carrying grains towards larger depths. So what you can do is a Lagrangian tracking of the front of this structure in depth and time to show that from the start of the experiments to the end, you have an inverse cascade from very small length scales to just one big plume at the end. And so this is a paramount conclusion. On purpose, I didn't want to do experiments with a pointwise source of sugar to see what motions they could create, because that would be like localized convection. I wanted as wide a mass flux as I could. And it turns out that fluid dynamics did its job of selecting a small wavelength to nourish compositional convection. But it turns out that because my tank is deep, the structures coalesce, and in the end, although I have a large uniform flux of grains, I end up with a localized flux of sugary water nourishing the motions in the tank. Okay, so this conclusion likely holds in the planet, but it's going to be dependent on the aspect ratio of the convective zone, the spherical geometry of the planet, and likely the planetary rotation. But still, this conclusion is also supported by what you saw with Ludovic, in particular in his experiments. You could see that we do not expect a uniform and steady flux of grains. So this picture is probably reinforced by that. So with this sugar, we nicely visualize the flow. So what we can do now is, again, fix the mass rate and just see the influence of the size of grains. So on the left-hand side, you've got big grains, and on the right-hand side, you've got small grains. On the left-hand side, the big grains have a low dissolution rate, so they remain there for a long time, forcing the flow by drag. And because this is drag forcing the flow, and because grains are partly decoupled from the fluid motions because of their own inertia, they constrain a vertical forcing, they constrain a laminar chimney at the center of the tank. Whereas when you have very small grains, they dissolve so fast that you can't see them here on this movie. And you can see that you quickly impart buoyancy to the fluid, which is capable of developing eddies. So there you have a fluctuating turbulent flow which develops. And this is just an effect of the size of grains because the mass rate is the same. So in the planet, it means that in the convective region, it is probably nourished by a heterogeneous buoyancy flux, and the flow is more or less turbulent depending on the size of grains. And also what you saw is that if you have almost instantaneous dissolution of the very small grains, then you can consider that the buoyancy flux is very local, it's at a certain surface. But when you have big grains, it's less the case, as you could see before. And to further support this, I'm showing this movie with very big grains, where you can see that they need to fall for a very large amount of time before they manage creating a plume at the center of the tank. And many grains are so big and they have so much inertia that they actually get closer to the plume. They are a bit attracted, but they never get inside. Okay, so there is quite a large decoupling between the motion of the particles and the motion of the fluid, and there distinguishing between a mixing layer and a convective zone is a bit more complicated. So for my last year of PhD, what I'm doing is I am finishing these experiments, of course. But then the other thing I wanted to do initially is numerical simulations, which could be used to properly model the particles and the phase change to then be included in the pre-existing numerical models so that we can then compute a possible magnetic field. And so to do that, I want to quickly show how I validated these numerical simulations. So what I started doing actually at the beginning of my PhD was not immediately reactive particles with sugar. I was using glass spheres falling in water, and it's just the fall of the particles which creates fluid motions. So the aim was rather here to study what's happening possibly in the snow zone. And as you can see with these experiments with a pointwise source of buoyancy, you have a cloud which is linearly growing in depth. And what you can do is you can compute the growth rate of the cloud as a function of the dimensionless size of particles. And as you can see, when particles are not too small, not too big, you have an optimum of the growth rate. The reason I'm showing it is because it's the most complex result we got. So we decided this would be a nice test case, which needs to be reproduced by an appropriate numerical model. And of course, modeling particles in a planet at a large scale, we can't do Lagrangian simulations. The costs would be absolutely huge. So I am modeling the particles as a field of concentration. What you can do is to consider basically two ingredients. Particles do not move as the fluid because of their inertia. A particle moves like the local fluid motion plus a constant settling term. And we saw on the movie before that the flow is created by the particles. So in the Navier-Stokes equation, you are forced to take into account the drag which the particle exerts on the fluid if you want to account for these particle-driven flows. And so here, under the formalism of a field of concentration, this is just proportional to the concentration. And so this model is very basic, but it turns out that it nicely reproduces most of our results, and in particular, this one, which is the hardest to get for the entrainment rate, for the growth rate of the cloud. So what you're looking at is 3D direct numerical simulations. I took a vertical section in the middle of the computational domain and superimposed the field of concentration at different moments just to show you the morphology. You do visualize that you get an optimum growth rate for an intermediate size of the particles. So this can already be implemented to take into account how particles move the fluid. And I need to add a reactive term now for buoyancy to go from the grains to the fluid. Thank you very much for your attention, and do ask if you have any question.
Thank you. Right on time. We have time for questions.
Hi, thank you so much. Great talk. This is Tina.
Thanks.
In your experiment, when you let those sugar particles drop onto the fluid, does this somehow influence also the motion that is later induced? I would assume that it's somewhat different to having particles settle through a liquid before and then just entering a new region from letting them fall onto a surface. That's just basically the question. Or maybe I got something wrong.
Yeah, so your worry is about what happens when they enter the fluid.
Yeah, exactly.
It's connected to that.
Yeah.
So during the movie, as you can see now, you can't tell exactly what's the initial velocity of the particles when they reach the free surface. But when you begin the experiments, what I can see is that particles stop at the free surface and then they enter because the surface tension prevents them from immediately entering.
Okay.
So this needs to be checked because at some point there is a very large mass rate. So maybe it alters that picture, but at least I can say that when I am capable of visualizing what's happening, surface tension stops the particles, so they have no initial fluid velocity.
Okay, thank you so much.
You're welcome.
Okay, thank you again. So we move to
Thanks.
Next talk is Jack Van Driel. He's going to talk about the composition of the Martian core.
Your PowerPoint or PDF? Great. Thanks. Thanks. Okay, can everyone hear me?
Yeah, so today I'm going to be discussing the composition of the Martian core through some atomistic calculations that we've been doing to invert for some of the recent observations from the InSight mission. So what do we already know about the Martian core? So this is the recent Staller paper from the InSight mission, where they estimate the radius of the Martian core, and it appears to be quite large. And the growing assumption is that the Martian core is predominantly fully liquid, but it may have an inner core. But for today's talk, I'm just going to be discussing an entirely liquid Martian core. And also from geodetic inversions, we've also got constraints on the density of the Martian core. And also, in terms of a chemistry point of view, we've also got some upper constraints, and for example, the sulfur concentration. But the elements I'm going to be focusing on today, this iron-rich core, would be sulfur, oxygen, and also hydrogen. So I'm going to be showing a range of density calculations and how these invert for the radius and the density. So I'm briefly going to talk about some computational methods we've done, the importance of magnetism when studying iron at low pressure. And then also I'm going to introduce this Gaussian regression equation of state, which we've been working on, which allows us to to interpolate across a wide compositional space and to invert for density. So for those who do atomistic calculations, we're doing the image on the left here is the snapshot of one of the calculations we're doing. Is iron, sulfur, oxygen, and hydrogen, and we're using a 64 atom unit cell, and we've studied 27 compositions so far, and pressures up to 125 GPa, and temperatures which are consistent with predictions for the Martian core, well, 2000 to 4000 Kelvin, and we're using the PV exchange correlation function. And all these calculations were performed in VASP. So magnetism is important, particularly in the case of iron, because iron atoms can occupy high spin states, particularly at low pressure. And these spin states reduce as a function of pressure. But at ambient conditions, it's suggested that iron has magnetic moments of 1 to 2 core-mantles per atom. And effectively, the consequences of having elevated spin states is that it increases the volume of your system and thereby reducing density. So it's very important when we're performing these calculations to fully incorporate the role of magnetism. And to do this, it's quite a complex procedure, particularly with iron. And so to estimate this, particularly in VASP, because when it reduces the energy per step, it doesn't include the magnetic entropy. So this is the really important thing we're calculating here, is to consider the magnetic entropy of the system. So to do that, we're using thermodynamic integration to calculate the free energy difference between iron at different magnetic states. So we start off with a system with have no magnetic moment, and we're calculating the free energy of difference of different magnetic moments. This then allows us to constrain the lowest energy, the system which magnetism which has the lowest free energy. And so once we've calculated this, we've got the magnetic moment as a function of pressure and temperature, and for an FES system. So these are a range of compositions and temperatures. So this is very important. Once we've got the magnetic moment, we then run the calculations at that magnetic state. So this just shows you the difference in compared to experiments of having the different roles of magnetism. So on the left here, we have a state where we don't consider magnetism, and we get densities which are elevated compared to that of the experiments here. So the red line basically is our estimated density from our Gaussian model, which I'll come to later. But essentially, if we don't include magnetism, we overestimate the density. We can then also consider the role of free magnetism. And free magnetism allows the magnetic moments to fluctuate freely within the system. But on the far right here, we've got the density as a function of constrained magnetism. So this is one where we've actually constrained thermodynamically the density. There's a relatively small difference actually between the free magnetic state and the constrained magnetic state, but it's particularly important at lower, slightly important at low densities. So now that we've searched for a range of different models, we can place them into our kind of global fit for composition. And so on the left here, we've got the range of compositions we've studied, and the blue lines are the calculations performed with no water content, and then green and red are the ones where we've increased the water concentration of the system. And then if we want to, actually constrain our calculations to match the explosive experiments, we can actually fit a separate model that calculates the pressure difference between calculations and experiments as a function of compositional space as well. So if for going forward, we're actually adding a pressure correction to get the correct density to reduce the density correction to match experiments. So the Gaussian regression equation of state that we've used searches all the compositional space, so ranging the sulfur, the oxygen, the hydrogen concentration. And on the left here, we've got an unknown composition. So during our fitting procedure, the regression hasn't actually seen this composition. And the aim is, if we want to fully invert the wide range of compositions we need to use, we need to make sure the model successfully predicts the correct composition. So this is the fit to an unseen composition. Density is a function of pressure and temperature. So once we've got our density compositions, we can start to constrain how well they fit to the density inversions of the Martian core. So the yellow bar here suggests the density required to match that of the insight inversions. And then here we just have the ternaries as a function of sulfur, oxygen, hydrogen, but also of water concentration. So when you have no hydrogen in your system, you need to have approximately 25, you have 25 weight % sulfur or 4% oxygen. Or you can have a much higher oxygen content and sulfur content as well. And as you increase the water content, it will obviously reduce the amount of sulfur and oxygen required in your system. And again, we can do this by moving up through the concentration of hydrogen in our system. So we go to 1% hydrogen, 1 weight % hydrogen. You can have 15 weight % sulfur or 4% oxygen. And also, if you have a lot of water, so 2 weight % water, you can have as little as 10 weight % sulfur. Irrespective, you need a lot of sulfur in your system and probably a lot of hydrogen in your system. So this is a quick summary. So magnetism itself is vital in reducing the difference between experimental results and calculation. And our Gaussian regression equation of state has allowed us to explore the range of compositions available. So at the moment, we've got 4 different chemical compositions, but this can already also be expanded to 5 or potentially more. The other advantage of using this equation of state is at the moment we are just constraining density, but it can be expanded to internal energy of the system. So in the future, you can potentially look at how composition affects the different adiabats for varying different planetary bodies. But already what we've seen is for the FES-OH system is that it's sufficient to adequately constrain, given our current constraints from the InSight mission, the density of the Martian core. This is going to be our favorite. I'll leave you with the favored model we've got for the Martian core, given its sulfur concentration. So you can choose what you want, really. There's a range of compositions available. Yeah.
Managed to gain some time, so we have time for questions.
So thanks for that. It looks like you're always going to get a trade-off between which light element is involved.
Yeah.
To reduce density. Is there any prospect of another way of having a different constraint?
Yeah.
What are the other constraints you could use?
I think from a kind of calculations point of view, I think the thing would be to calculate the heat capacity and then the thermal expansion. So then you can get different adiabats for different compositions, and then you can see if some of those some of the compositions with maybe really 2% hydrogen might give you quite extreme adiabats, and then they might say, okay, you might have a solid core, for example. And so I think you need to expand it to include more of the kind of numerical models we've seen today, and just to see how those fit, because it might, if you have a crystallization of a Martian core, then actually your density might mismatch as well. So I think there needs to be more of a kind of extensive approach. If that makes sense. So I think you need to kind of include the results, so also the viscosity as well, so we can kind of interpolate the viscosities and the different adiabats.
They then sort of feed into a thermal evolution model, and you need the thermal evolution model as well as a thermal.
Yes. Yeah. I think that's probably the way I would proceed.
Hi.
Yeah.
Thank you for the talk. You say that this range of compositions that you've shown are consistent with geochemistry.
Yes.
Are they all? I mean, I'm definitely not a geochemist, but I know that geodynamicists and geochemists barely agree. So I'm wondering, is it reasonable to have such huge amounts of oxygen and Martian core?
The oxygen I think you could get down to about less than 4% oxygen. I mean, that's what I would favor the sulfur side of the diagram and not the oxygen side. I think there's a limit on the on the highest amount of sulfur you can have. So you're probably not going to have more than 15 weight % sulfur in your system. So I think it's going to come down to these two kind of phase diagrams, whether you want to have more water. I mean, the water is also the problem. So when you want to start having a lot of water in there, then I think that's going to be a question, because 2 weight % water is a lot of water. So, I mean, it's a huge amount of water. And even 1 weight % is quite a lot of water as well. So I think when I say it's consistent with the sulfur concentration.
I have a quick follow-up question, but under which conditions do you put that much? Can you put that much or many light elements into the core? I mean, yeah.
So
Mars is a small body, right?
Yeah. So I think that's the next kind of leading on from what Andrew said, is the partition coefficients is getting that much light element in the core as well. So we haven't calculated the partition coefficient getting that much light elements at those pressure and temperature conditions.
Okay, we have a question from online from Attilio. To what experimental data did you do compare your liquid FEH calculated properties?
I haven't done the FEH compared to the FEH. I mean, there's an FEH. Where is this? The FEH, the liquid FEH it's in terms of literature, it's not particularly well constrained. There's an iron hydride, which a lot of the inversions are typically done on solid iron hydrides, and not necessarily on experimental Fe iron hydride. So
yeah, thank you for a good talk. You we're occasionally conflating weight percent water and weight percent hydrogen.
Oh,
Assume
sorry,
when you have two weight percent H, that's weight percent hydrogen.
Yeah.
That is 50 atomic percent
Yeah.
hydrogen.
Yeah.
Is that a reasonable amount?
No, I don't think two weight percent hydrogen is, realistic. But I mean, we've just got to calculate the. I mean, in terms of the density, it's, but in terms of the wider consequences of that, yeah, I think it's unrealistic. But you need to get the density down. So and you've got a limit to, you've got a maximum amount of sulfur. So you've got to have, you can do that with 1 weight percent. Yeah, I'm not saying that it's not an insignificant amount of hydrogen, but you need to have something to get the density down. If that's what the density is, I mean, yeah.
Jack, I have a technical question.
Mhm.
How do you do your thermodynamic integration from non-magnetic to magnetic?
So I set 2 different magnetic states of the system. So I have an iron free and an iron, and I define the magnetism in my constrained magnetism. So I set it to be 0.5. Yeah. And then so that gives me my delta H, my difference in the Helmholtz free energy. And then I also calculate take those individual magnetic moments and put that in. So I have 2 separate, I have the vast way of calculating.
When you do your lambda,
yes, yeah.
The lambda, say 0.5, that has to mix half of your magnetic system and half of your non-magnetic.
Yes.
You have to calculate the forces from both.
Yes.
And mix them.
Yes.
And then evolve all those forces.
Yes. So I mean,
that's how you do it?
Yeah, and that's, I mean, I use the kind of the vast method. So you have different lambdas. So I have a lambda of, I vary the lambda between 0 and, so this is my, so I vary my lambda from 0 to 0.5 and 1. And then I integrate under to get my, the delta H of between those two.
That's not automatic available.
Yeah. We can talk about this later. Yeah.
Okay. I think we have, we managed to get back on time. So we conclude the session of the morning and we'll come back in an hour.
And my apologies to the online participants for the hiccup with the slides there. The talks are recorded, so you'll be able to access the recording later on. Thank you.
Okay, so our first talk this afternoon is an invited talk by Charles Hettard Bukhari, I think, on Beyond 1D Magma Ocean Models.
Good afternoon, everyone. First of all, I would like to thank the organizer for giving me the opportunity to present my recent research today here in London. So today I'm going to talk about some application of multi-phase flow physics to early mantle dynamics. So the main motivation of this research, let's say the general context of this research, is to better understand the very early stages of our planet. And so the idea is to provide some constraint on this transition during this magma ocean era, where the mantle crystallized, so moved from this molten state to the solid state. And there are two major implications for the long-term evolution of the Earth. The first one is depicted here by these different layers of different colors. That's the early differentiation of the Earth, so the formation of geochemical reservoirs of distinct composition that might have a long-term, that might be observable today. And the second aspect that is depicted here by this kind of pseudo-dynamics is the role of these primordial heterogeneities on the long-term mantle dynamics. So these two major questions actually raise several, let's say, sub-questions. The first one is, how does mantle solidification proceed? So we talk a lot this morning about this issue of bottom-up crystallization, top-down crystallization, and actually this kind of new crystallization scenarios that has been first postulated for the core now, well, were applied to the mantle, actually not much long time after it has been proposed for the core. And so there is this question for also the Earth's mantle, whether the Earth crystallized from the bottom to the top or from the top to the bottom. Another important question is the degree of mantle differentiation after magma ocean solidification. So the question is actually, do we really form reservoir of distinct composition? So the magma ocean models has been built for the moon, where we have evidence for a strong differentiation during magma ocean crystallization. But is it a general case for all planets? And in particular here, we're going to focus on Earth. Would the Earth's magma ocean crystallization would produce a strong differentiation? So reservoir with really different composition. What is the initial degree of mantle mixing after magma ocean solidification? Again, in the first model of magma ocean evolution that has been proposed for the moon, we have this kind of first order cartoon where we have layers of distinct compositions that are just stacked on the top of each other. And actually recent models have shown that we might have an early mixing of this primordial layering that would have an effect on the preservation of this primordial heterogeneity through time. And again, in general, what would be the role of this solidification on the long-term solid state mantle dynamic? And we might also argue on the current structure of the Earth. Can we have like some relics of these early stages of the Earth dynamics that we can observe today in its like seismic structure? So there is a kind of paradox that we need to solve here regarding this magma ocean era, is that on one side, we have argument in favor of an ancient magma ocean, and we have some kind of signature of primordial differentiation, for instance, thanks to short-lived radioactive isotopes. But on the other side, if we consider the, let's say, the most simple case of crystallization or fractional crystallization, we end up with extreme geochemical reservoir from a geochemical perspective. So let's say we're going to observe composition or rock compositions that we're going to end up with compositions that we do not observe in current rocks. Or from a geodynamic perspective, we will form layers, really dense layers, for instance, that will be enriched in iron oxide that must be preserved on a really long time scale, and we do not observe such really intense layering at the deep in the deep mantle. So we need to find a solution to solve this paradox. And actually, our proposition and what I'm going to talk about today, it's nothing fancy, it's just something in between the two, that we can have some kind of fractional crystallization, but we will lie in between this end member of batch crystallization and fractional crystallization, and the free dynamics, actually, the convection, the thermocompositional convection that would be associated to the phase change might dilute a little bit potential strong fractional signature of the crystallization. So I have entitled my talk Beyond 1D Magma Ocean Model. It's because up to now, most models that treat magma ocean evolution relies on 1D model, where the only dimension that we want to capture in this dynamics evolution is the depth. So here I'm showing you a typical example of 1D thermal evolution models that are really similar to the kind of models that has been presented this morning for the core. So here you have the depth on the horizontal axis, the temperature is the vertical axis. And basically you're going to use this model to capture the thermal evolution of the magma ocean. How much time does it take for the magma ocean to cool? So here the adiabat, or the temperature in the mantle, is depicted by these black lines. And so you see as time goes, so the magma ocean cools. And one important aspect and one important result that we get from this model is where the crystallization should start. So again, for core evolution, we discussed this morning. So the depth at which the adiabat intersect with liquidus will define where we expect the crystallization to start. So for instance, in this kind of model, the adiabat here intersect first the liquidus in the deep mantle. So this kind of model would suggest that crystallization proceeds from the bottom, from the CMB to the top. So once you have this thermal evolution model, you can couple them with some kind of metrology or a bit of chemistry. So here now, the horizontal axis depicts the pressure. So the surface of the planet is on the left here, the CMB on the right. And so at different depths, at different pressure, we expect to crystallize different minerals. So the compositional evolution of the magma ocean will essentially be controlled by the minerals and the partitioning coefficient between the melt and solids. And so let's say that here we consider a scenario where crystallization start to crystallize from the CMB to the surface. We're going to first crystallize from Bridgmanite. So relevant partitioning coefficient will be partitioning coefficient between Bridgmanite and melt. And as crystallization proceeds from the bottom to the top, then we're going to start, let's say, at the end, olivine or wapsleite. And now, if you want to track the oppositional evolution of the magma ocean, you need to take into account this low pressure mineralogical phase. So today we're going to try to move beyond this 1D model, but we will have to make other assumptions to make our model reasonable. So the advantages of 1D model is that actually it's the only option to capture the magma ocean evolution in the really early stages of the dynamic, where the melt fraction is extremely high, because during these early stages, the vigor of convection is really high. So heat transport by convection is extremely efficient. And this regime of really turbulent convection cannot be captured by fluid dynamics model. Even in experiment, it's extremely challenging to reach this, this regime. So we relied on 1D models that can capture this heat transport efficiency using some kind of eddy diffusivity or parameters that can capture these time scales of cooling. However, there are some limitations of these models. For instance, we cannot approach lateral thermochemical variation. That could be important if we want to discuss the structure of the Earth mantle at these stages. Most of the time, this model neglects compositional convection. And most importantly, we made some assumption about the multi-phase physics, and in particularly the efficiency of phase separation. And actually, this is going to be phase separations that are going to control the efficiency of the formation of mantle heterogeneity or the efficiency of differentiation. Basically, if you want to have a really strong signature of differentiation, you need to have a melt that is perfectly extracted from the residual solids. And if you want to somehow mute the fractionation signature, you want a melt to basically crystallize in place inside the matrix. And so this problem of multi-phase physics becomes really problematic when we're going to reach this rheological transition where the melt fraction will drop below 50% of melt, so the late stage of magma ocean evolution. So this is a kind of simulation that I'm developing. So an important part of my research is dedicated to the development and to advance this kind of numerical models. So here the idea is to bridge the gap between this 1D model and solid state mantle dynamics. And one specificity of my approach is that my mathematical model, and so my numerical code, can handle melt fractions that ranges from 0 to 100% melt fraction. So this specificity allows me to model regime where melt can be extracted in regions that will be, let's say, fully molten during a short amount of time, and that my code will not break. Because for people who are aware of this kind of multi-phase flows, this has been developed for quite a long time in the geoscience community, but usually we treat really small melt fraction. And because the equation has been developed to treat small melt fraction. Here, I want to be able to treat really large melt fraction. So today I'm going to walk you through simulation like this one, where here I'm showing you the temperature field. Here's the melt fraction field in 2D. So basically green means fully solid. Blue, it's a mush, so at about 50% of melt fraction. And when it's totally white, it's going to be 100% of melt, so fully molten. We're going to track the evolution of the composition. And here we're going to follow, in the first slide, mostly the iron oxide content, because this would have a really important implication on the density of the material for both solid and liquid, but also on the melting curve of the silicate, because iron oxide is known to decrease the melting temperature of silicate. And so you can now anticipate a bit the amount of feedbacks that we can have in the flow between crystallization that will generate compositional variabilities and this phase change. What I'm saying, yeah, phase change is going to generate compositional variabilities, and convection is going to try to mix all of these things. So basically, the objective of this model is then at the end, try to end up with structures like this that might be consistent with what we observe today at the bottom of the mantle. So here I'm showing you really specific simulation where the differentiations that we obtain at the end of the simulation allows to have a mantle that is mostly homogeneous, but with some dense region that are enriched in iron at the bottom, and with some regions that are molten, extremely enriched in iron at the core-mantle boundary. So today I've divided my talk in 4 parts. The 2 first ones are quite small. I'm gonna briefly present my mathematical and numerical approach, just the broad concept. Then I'm gonna present the main dimensionless numbers that control my simulation and that are important to understand the fluid dynamics that I'm describing today. And then we're gonna go to 2 implication, one for the geodynamics. We're going to discuss the formation of a basal magma ocean from a fluid dynamics perspective, and then the long-term dynamics of an heterogeneous mantle. So if we form early on mantle heterogeneities, how they can be mixed and interact with the basal magma ocean. And then I'm going to present you a really preliminary work on the implication for the geochemistry of an early form basal magma ocean that can be captured by this kind of fluid dynamics model. So let's start first with the mathematical or numerical approach. So if I want to use fancy terms, we can say that what I'm doing is I'm solving double diffusive thermochemical convection with phase change and phase separation. And I'm assuming for now 2D Cartesian geometry. So this might look a bit fancy, but there is nothing really difficult here. And we have talked a lot about this process actually this morning. Basically, in my numerical simulation, I have two velocity fields, one in red here that I'm going to call the mean flow. So this mean flow is the mean flow of the mixture of both the liquid and the solid. And this mean flow is driven by thermal density contrast. So here, my box is heated from below and cooled from the top. But I have also compositional density contrast that drives the flow. That would be due to either the presence or the absence of crystals. So crystals can make the mixture on average denser or lighter than the surrounding fluid, but also the iron content of this given parcel of fluid can also affect the bulk density of the fluid. On the top of this like mean flow velocity field, I have another velocity field that I'm going to call the phase separation velocity field that constrain the how fast crystal can segregate from a melt, let's say, but I would be more interested here by how fast a melt can be extracted from a mushy zone. And so if I consider only this thermocompositional convection with this two velocity field, I would have a constant crystal fraction. So to change my crystal fraction, I need another like ingredient that is melting on solidification. So I have a parameterization of phase change based on self-consistent phase diagrams that allows me to track the evolution of the crystal fraction. So here I'm going to consider only thermodynamic equilibrium. I'm gonna skip this slide because I don't want to bother you with equation, but we can come back to it later if we need. So governing dimensionless numbers. So what I want to do here is try to explore parameter space with dimensionless number that characterize the flow. And so as you can imagine, there are many dimensionless numbers that are involved in my mathematical formulation. But here, actually, you need to understand just one dimensionless number to follow my talk today is this dimensionless number that I'm going to call the melt mobility number. This melt mobility number describes how easy it is for a melt to be extracted from the matrix. And basically, this melt mobility number depends on the crystal size, viscosity at first order. So low melt viscosity will allow easy extraction of the melt from the residual matrix. So keep this number in mind because we're going to use this number to actually go from a dynamic regime where phase separation is easy, where we're going to create extreme compositional differences, and to regime where phase separation is inhibited and we won't have any differentiation. So this is one aspect of the formation of mantle heterogeneities, but actually we have a competing aspect that is a reentrainment, because all my system here, my magma ocean is convecting. And so there is a possibility that this phase separation is counterbalanced by reentrainment. And so at first order, actually what would control the amount of differentiation is this competition between velocity of phase separation and the velocity of the mean flow. And so at first order, chemical differentiation is expected to occur if phase separation is at least as fast as convective motion. And here again, what I mean by convective motion is the convective motion of the mean flow. So I've talked in the previous two slides about the formation of mantle heterogeneities. Now, if we're interested in the preservation of these mantle heterogeneities, how easy it will be for these compositional differences to be preserved in the mantle. We have to talk about this compositional density contrast, because that's going to be mostly the difference in densities, and that will allow, let's say, an early form dense layer to be preserved on a long time scale. And here I have two dimensions numbers that controls this density contrast, one that is associated to the density contrast between solid and liquid, and one that is associated to the density contrast between iron-rich end member and magnesium-rich end member. And we have to keep in mind that it has been shown that density contrast between melt and solid can change with depth. And so here I'm using a parameterization that can capture this aspect. So let's move to the first part. We're going to talk mostly here about the geodynamics and the fluid dynamics of first basal magma ocean formation. And here I have three messages that I want to give you today. So the first one is that basal magma ocean forms by accumulation of iron-rich silicate at the core-mantle boundary. And what has been proposed first as the intersection between liquidus and adiabat to be the driving process to drive whether we have bottom-up or top-down crystallization is not enough. And actually, we can form this basal magma ocean just because actually iron-rich stuff are dense and will sink. We can control the amount of chemical differentiation by this met mobility number, as I said before. And another really important aspect is that, as opposed to previous model, here when we solve thermal convection, we can show that actually crystals form first at the surface of the planet and not in the deep mantle where the liquidus and adiabat intersect. Actually, the liquidus and adiabat also intersect at the surface of the planet, because the surface of the planet is so cold compared to the interior that there is a thin region where actually the temperature is below the solidus. So we're going to see that now in simulation. So I'm going to start here with a simulation where the mobility number is really small, and again, small compared to the velocities that are produced by thermal convection. And so in this simulation here, again, on the left, you see the met fraction, on the right, the composition. Since the met mobility number is really small, I do not form strong compositional differences here. My mantle is almost homogeneous. Okay. So now we're gonna move to another numerical experiment where now my mobility number is really large. So my phase separation will be efficient. And so we'll see that I start to form right away iron-rich region. And so iron-rich region here in red start to accumulate at the bottom of the mantle because they are dense. And you see here that some of them are molten. So here white, but most of them are still solid. And so it's just with time that then this actually iron-rich solid will remelt to form a basal magma. Yeah. So if you had really good eyes, you might have seen that, as I said in the first slide, crystals here form at the surface of the planet in cold downwelling plumes where the temperature is below the solidus. So crystals here first form at the surface and then they sink. And some of them, like I have not quantified how much remelt, but I can see that there are some remelting here. And early on in the simulation, remelting is important, but when we reach the end of the solidification where the temperature is closer to the solidus, now there is almost no remelting. So compared to previous models that have shown that crystal form where the liquidus intersects the adiabat in the deep mantle, actually this condition only controls where they can accumulate in the mantle, but not where they form originally. So in the last part, I'm going to talk about potential geochemical implication for this shallow crystal precipitation. Now let's move to the second subsection where we're going to talk about the long-term dynamics of an heterogeneous mantle. Heterogeneous in the sense that we form region with different iron oxide composition, and the solid mantle is in interaction with a basal magma ocean. And so here I have two messages. The first one is that if we have a really large melt mobility numbers, we're going to end up with extreme mantle differentiation that cannot be rehomogenized by mantle convection. This is not a new result, but that allows to somehow bracket how much differentiation is allowed, is reasonable from a geodynamic point of view. And so if we decrease this amount of phase separation, we can find regime where we have a mantle that is not too much differentiated and that might be a bit more consistent with the current structure of the Earth's mantle as seen by seismology. So to illustrate what I've just said before, I'm gonna take these simulations that I stopped in the previous section. So here it's almost the end of the first stages of mantle solidification where the upper mantle solidified. And so let's say that I keep running my simulation to see how these heterogeneities mix. Well, actually, they do not mix because here the compositional density contrasts are so large between, let's say, a magnesium-rich upper mantle, quite rich, iron-rich lower mantle here with about like 10%, 12% of iron oxide, and with an extremely iron-rich basal magma ocean, which is about more than like 25% of iron. So in that case, we end up with a mantle structure that is not consistent with what we observe today with seismology. But if we decrease a bit this amount of phase separation, now we can end up with a model where the compositional differences that we have in the mantle are not too large, so they can be entrained and mixed by thermal convection. And so in that case, we end up with a structure, a compositional structure more like this, that might be more consistent with what we observe today. So that's the second result. When we increase this phase separation efficiency, we go from an homogeneous mantle, basically, to a mantle that is strongly stratified. Okay, so now I'm gonna go to my really last part, and it won't be too long. It's preliminary work where I wanted to now constrain this amount of differentiation with a bit of geochemistry. So in this previous part, my main concern was to end up with a compositional structure of the Earth that is consistent with geodynamic and seismology. Now I would like to be consistent with geochemistry, because this amount of differentiation, we're gonna partition a lot of elements, and the idea is to see how much partitioning would be consistent with what we observe today in terms, for instance, of trace elements. So I have two main questions here that I would like to address, and here for now is mostly like questions and not results. The first one is, what would be the implication of a low pressure crystallization of a magma ocean at low pressure at the surface? So these crystals that first form at the surface and then sink, compared to a model where crystals mostly form in the deep mantle. And the second one, as I just said before, is how can I constrain the amount of mantle differentiation? Can I have an external constraint on this melt mobility number? So one way to tackle this problem that I'm proposing here is to use the partitioning of refractory lithophile elements, because they do not partition the same way with low pressure phases, let's say between olivine and liquid. They do not partition the same way as at low pressure than at high pressure. And for instance, there are some elements like potassium here that are strongly incompatible at low pressure, but become compatible with bridgmanites at high pressure. So to me, that could be a kind of test that I can use. So implement these partitioning models to see whether the geochemical structure of the mantle that I obtain at the end of a simulation will be consistent with one or the other scenario. But we can go and use actually other like geochemical tracers, because what is nice with numerical experiment is that once you know how to advect one propositional field, I can put like as many as I want. It's not expensive to advect like quantities. And so there are many like geochemical ratios that I could use to test this model. And so basically here I'm showing you different geochemical ratios that have, each element have its own like partitioning coefficient. And here I'm comparing at equilibrium, the composition is of the melts in equilibrium with the solids. And so it's all normalized by the ratio of the bulk silicators. So let's say my starting composition. So for the melt, it all starts at 1, because if at the beginning of my simulation, I have no solids, everything in the liquid phase, and I have not segregated the liquid from the solid, so everything is at 1. And same thing for my solid. At the end, if I have not extracted any melt, I should go back to 1, so the reference composition. But here you can see that, let's say I form this first solid here, I have strong fractionation of this solid. And so if I remove them from the melt, I can form solids that are kind of weird compared to the bulk silicators, and try to see if I can preserve this kind of solid on long time scale. That's what I'm currently doing. So basically I'm coupling now this geodynamic evolution with geochemical tracers to see the composition of these reservoirs that are formed by the crystallization of this primordial magma. So thank you very much for your attention. I'm gonna stop here.
Thank you very much. Do we have questions?
Continuing my line of not very bright questions, go back to slide 1 or slide 2.
1 or slide 2.
Yeah, really early. So what woke me up was you had, when you're, no, that, one with the cartoons.
Oh, the 3, okay, okay, that one.
Yeah. So you have on your gigayear timescale, I mean, gigayears.
Yeah.
But you've got a separation of core and the mantle.
Yeah.
To start off with.
Yeah.
Now, when I've been teaching my students, so probably wrongly, you know, we've had the mantle and we've had diapirism and rainfall and all sorts of the core coming out of the mantle. So is it really fair to split them like that, or isn't something happening between them to start off with?
Good question. It's depends on the relative timescales that you consider for the formation of the core compared to the timescale of the cooling of the magma. Like diapirs can like sink quite rapidly in the liquid magma ocean. So in that case, it would be fair to have, let's say, first core formation.
So actually, yeah, 0.1 gigayear, so that's 100 million years. So you've had a giant impact come up and it's kind of messed everything up and then it's separated. But the mantle presumably would have evolved a little bit during that time anyway. In the first 100 million years, it wouldn't just be sitting there as a uniform magma ocean.
No, true. But then it would, the question, so if I'm following you, would be, do we have a signature of what's going on before a giant impact?
Well, no, I mean, it's not even that. My question is that I find your initial condition
okay,
unduly simplified, and
I see.
There would be interactions happening which would also affect your later conditions in the generation towards that initial condition.
I see. So no, I agree with you. We could have some interaction of the silicate with a metallic phase.
But it's not even interaction. It's the fact that your mantle is evolving during that time as well.
So I should consider.
It's not clear to me that you've got a kind of your naught gigayears, which I'm assuming in practice is 100 gigayear, 100.1 gigayear in time. That kind of split between the two and the uniform mantles seems there could be some additional complications.
Okay, I see.
So we've got a couple from Helen Williams online. What controls the magnitude of H in your melt mobility parameter, and how do you constrain this?
The magnitude of H. Oh, this H, this big H here is the length of reference of, well, it depends how you non-dimensionalize the problem. So where I non-dimensionalize it, here it's the size of the mantle.
Okay, so that's just the thickness of the
mantle. Just the thickness of the mantle.
And the second question is, have you considered outgassing of the atmosphere near the surface, the crystallizing magma ocean? What would the implications be for the insulation and the timescales of crystallization with insulating atmosphere outgas?
So if you have an atmosphere, you might delay, you increase the timescale of the cooling of the magma ocean. So now it's like you have more time for the magma ocean to have phase separation, because you can have an end member where you solidify the magma ocean so rapidly that you do not have any time for separation to occur. So that would be one.
So maybe a phase separation is more important.
Would be more important in that case. Or at least would have more time to act. Yeah.
And what's D here in?
At the top, its temperature is imposed. Temperature is imposed at the top.
Which boundary condition are you using here? So you fix the temperature.
I fix
so
the
you don't
temperature.
have like a flux boundary.
No, it's not a flux boundary. Yeah.
And just quickly, how do you define your crystal size here, D?
Okay. Good point. So I'm rather agnostic regarding this crystal size here. I'm just varying these delta parameters, this delta value, that is my melt mobility number. So then your question would be, well, if I need to answer the question, I would say, okay, I need to choose to pick a melt viscosity value, a US value, and say, okay, in this condition, these delta values that I'm using correspond to this size of this crystal size. But in my simulation, I'm rather agnostic. What does matter in my problem is this ratio of these quantities.
I was just wondering, you mentioned kind of comparing your model to current seismological information that we have.
At the very first order.
I was going to say, if you've got the temperature and you've got the composition, is there a way that you can kind of estimate your various seismological kind of like slowness or quickness comparatively? Or
I would not push that comparison to that level with like to quantify really the difference. I'm already happy that, qualitatively speaking, I end up with, let's say, structures that kind of make sense. But dynamic of the lower mantle is a way more complicated than the ingredients that I'm putting here. You have, this viscosity variation due to many parameters, and this is not something that I'm capturing here. So that's why I would not try to push the comparison too far.
My question's been stolen, so you don't have to answer it later. Okay, yes, thank you again. Next up, we've got Maxim Bauer. Who's also talking about basal magma oceans.
Yeah, kind of taking off where Charles-Edouard stopped. So yeah, this hypothesis has now been introduced. I'll let you have a look at the nice cartoons which kind of explain it. Also the idea that the ULVZs are remnants of the BMO for basal magma ocean. And yeah, it's kind of interesting because it sets up the initial condition for mantle convection and mantle structure. It has also been suggested that a BMO might have been formed and still be present on Venus and in the present day and on Mars. Various ways to make a basal magma ocean. Charles Edouard also mentioned that he looks at these end members of fractional crystallization. Then you would just separate a basal magma ocean and you would crystallize the top magma ocean bottom up, and a basal magma ocean would crystallize much more slowly. And there are slightly different scenarios here. I'm going to go into detail. For batch crystallization, I get here laser pointer. For batch crystallization, well, this is not really pure equilibrium batch crystallization, but more what Charles Edouard talked about in terms of the two-phase flow and compaction. And in that case, you would get a more iron enriched basal magma ocean. And the other option is that you just crystallize bottom up the magma ocean, the top magma ocean. Then you get an overturn. This is also kind of a scenario that Charles Edouard in one of his end members. And then you get remelting at the bottom. And in this case, your basal magma ocean might be also enriched in silica, because you're kind of overturning the protocrust, primordial crust. So this might be some chromatic composition or something like that. But the bottom line is there's many ways to form a basal magma ocean. You will always form it regardless of where the adiabat intersects the liquidus. And it would be variable in size and composition. This is something we don't really know. So these are just the scenarios A, B, and C. So this is basically taking off where the last figure that we saw also during questions from Charles Edouard, where he still had a BMO around, but that BMO would then crystallize by fractional crystallization. The BMO is long-lived, and it's very hard to extract heat due to the overlying solid mantle. So the BMO should really crystallize by fractional crystallization. Whereas for the top magma ocean, there are several scenarios, which I just mentioned. So the problem is it gets more and more enriched in iron. So I think if you would run the snapshot where Charles Edouard stopped for longer, then you would end up actually in the same kind of problem, where if you keep on going here using actually Charles Edouard's thermodynamic model, if you just keep on going and crystallize a BMO of thickness here, just non-dimensionalized, so let's say 200 kilometer thickness, then you would get a 30 kilometer extremely enriched layer at the bottom, which is not consistent with the so this is basically iron end member, close to iron bridge monad end member, and you would have density anomalies that are outrageous, right? 1,500 kilograms per cubic meter. And this is something we don't see in Earth, maybe in other planets. We don't know yet. Yeah, Mohammed has a poster on this, explaining this in a bit more detail. And now I cannot I have to go back to the mouse. Then I can fast forward this simulation. But actually, it shows that first the cumulates are entrained, then you get intermediate cumulates, which are forming. This is basically where Charles Edouard stopped, or somewhere here, where the basal magma ocean was still around, and then you make these piles. But in the end, you get this extremely iron-rich layer here in blue. And again, the compositional density anomaly is shown. So this is inconsistent with the present-day mantle structure. All these yellow bits might be consistent, but the blue stuff so at face value, the BMO should be still around, because something that is so iron enriched should still be molten at present day CMB mantle temperatures. So how to reconcile the BMO crystallization with the present day Earth structure? That's kind of the question I'm asking here. The first thing I was thinking about, okay, the BMO is, the basal magma ocean is sitting there, but the mantle is above, right? There might be some chemical interaction between the two. So just at the boundary, and let's switch back on the laser pointer. At the boundary in this pink box, there's this kind of, I could just call it the bulk composition. The bulk composition of the boundary is somewhere between the mantle composition here in this ternary diagram and the BMO composition. So let's just say, so this is just one of these scenarios. I think it's the last scenario, which also Charles-Edouard preferred, that the BMO starts over here. This is your bulk composition. This is the composition of your cumulates you will extract and train into the mantle, and the remaining liquid will be over here. So your BMO will evolve in that direction. So if you consider pure reactive crystallization of the BMO, you will keep on doing this, and the BMO will just go in this direction, and just follow basically the isotherm there. One scenario for very efficient interaction between the BMO and the overlying mantle is discussed in this paper by Daniela Borjau and co-workers. So the BMO evolves and just hits at some point the eutectic here in this ternary. Then the cumulates will suddenly resemble more like an enriched mantle composition, an enriched pyrrolite. So pure reactive crystallization should predict this kind of two-step cumulate sequence. But of course, you will have also cooling at the same time. At some point, you will also have cooling, depending on the time scale of this reaction, which kind of depends on how well you entrain these cumulates and bring fresh material to the boundary. You will have both, and the reality might be somewhere in between. And in the end, this is again pure fractional crystallization. You will still go down into the eutectic, so that's a problem. I already mentioned that. So the density anomalies are just too high, and this materials will never be entrained. And now notice that I've plotted this here for this expected eutectic, which in a real system, not in a ternary, should be further to the left, particularly in an aluminium bearing system. In this BMO reaction scenario, you will, depending on where you start with the BMO composition, you will also end up in the eutectic and cool at some point. Depending on how fast you cool, you will have a different trajectory here. But actually, at some point, you will stop evolving down into the eutectic because at this point, this is kind of the point of return, let's say it like that, not the point of no return. But here, if you add mantle into the BMO, but remove cumulates from the BMO, which are in in equilibrium, like these cumulates here, 3, or they would be slightly more iron enriched. You remove these cumulates from the BMO, then then the system is kind of happy, and you can actually start to crystallize the BMO, and the BMO will shrink. So anyway, there was one thing we didn't like about the scenario, and I will come back to that later. So we looked into an alternative scenario, which might be actually much more efficient. So we thought, oh, well, the mantle is actually heterogeneous. There is crust everywhere, right? Basaltic crust that is subducted, and some of it is recycled. And maybe at the most of it will settle at the core-mantle boundary because it's dense, or I should say at the basal magma ocean, mantle boundary, or BOMB, if you want an acronym. And it might partially melt there, or even fully melt there, depending on temperatures. And that there, even today, the more solidus is very close or below the current core mantle boundary temperature, depending what that is. At least in the Archean and the Hadean, this subducted crust, or maybe not, we didn't maybe have subduction, but we had some kind of dripping, would be molten or partially molten. And then, of course, the interaction between two melts is much more efficient than between a melt and a solid. So we basically just we just mix these two melts, because that basaltic melt should be, particularly if it's a partial melt, should be denser. So the mixing should be very efficient. And we even today we deliver a lot of well, this is a phanerozoic, a lot of crustal material. So if in the Archean and Hadean that would have been similar, but I expect it to be actually more. The delivery of crustal material should have been more efficient, I think. Well, but even that as a lower bound, maybe the time scale of reactive freezing due to this process would be on the order of 1 billion years. So it's shorter than what has been estimated for fractional crystallization due to cooling, which is 2 to 3 billion years. So what do we get here? So in this case, just because it's easier to visualize, let's start over here. The BMO is a pyrolite. That would be the scenario A. And of course, we just mixed in this subducted crust, basically. So we evolve in that direction. At some point, we mix in partially molten subducted crust. So it's kind of intuitive in which direction the BMO evolves. And it also grows in that process, I should say. So BMO starts growing in the beginning. It also becomes more alumina enriched in that process. You add subducted crust and you remove MgSiO3 essentially. So that some point you will drive iron disproportionation. So you have a aluminium oxide that will react with a FeO, and then you will actually drive iron out of the core, out of the BMO and into the core, which is one way to get out of that problem that we have with the BMO and the cumulates eventually being too enriched, right? And you also produce some ferrous iron in the well, it's not bridgemanite. It's still molten in the basal magma ocean. So yeah, eventually you do something similar as on the other side, but once you reach this point, so this is the point of return on that other side of the phase diagram. The cumulates, well, this point should actually be somewhere here. The cumulates are more iron enriched than subducted crust. So what you add is less iron enriched than what you remove. So you start to shrink. The basal magma ocean will start to shrink in that process. And as long as you keep on going, you will keep shrinking it quite efficiently. And rather soon, maybe after 1 billion years, at the very least, you will, be just left with the ULVZs, and those ULVZs will have the composition of subducted crust. So that's a prediction of this model. So you will have again a two-step cumulate sequence. In this case, this is like a bridgemanite, and this is not bridgemanite plus ferropericlase as in the previous scenario, but it's an aluminium and enriched and ferrous iron enriched bridgemanite. So we can compare the two scenarios. Both scenarios kind of might be consistent from the density point of view with first forming a candidate material that is entrained, strong, and might be a good candidate material for these beams, which have been proposed. I'll refer you to these papers. I'm not going to discuss that in detail. And the LLSVPs, which have already been mentioned. So how do we test them? The difference, of course, is here between light blue and light green. And there is, based on some geophysical constraints, there is a paper by Kenny Vilea and co-authors who estimated the LLSVP composition, and it's kind of a probabilistic inversion. So they come up with a range of compositions, but they can pretty much rule out that there is a lot of ferripagged clays. So you see this trade-off between bridgemanite and calcium perovskite. So there is bridgemanite and calcium perovskite in the LSVPs, but not much ferropericlase. So that kind of already rules out scenario 1 reaction with a pyrolytic mantle. And there's also a lot of Al2O3, a high oxidation state, strong oxidation, also ferrous, a lot of ferrous iron, which kind of supports the second scenario. This is just the last slide. If we buy into that second scenario, I'll bring it up here again. So for those of you interested in geochemistry, there is a lot of interest in, for example, the relationship between the short-lived tungsten. This is the daughter product from a short-lived thorium, hafnium isotope. So the tungsten anomalies, and there is a relationship here in hotspot lavas with the helium anomalies, and there are also other noble gases that have been studied. One candidate material, and there might be questions, there might be also some geochemists have invoked core-mantle interaction, which might be another interesting scenario, or maybe core BMO interaction, which might be more efficient. But there are also these other. So there's also other options where these observations might be explained by the last remnants of a basal magma ocean. For example, the composition of the prediction, as I mentioned, of this model is that the ULVZs have this kind of composition over here. So that could be compared to seismic observations. And it could also be tested if they would have an enrichment in terms of the geochemistry. Okay, there was another slide, which I forgot. So, so in Venus, I think also so I disagree with a paper by O'Rourke. I think due to the episodic resurfacing, the reactive crystallization should have been very efficient. So there should be no BMO on present-day Venus. On Mars, there is a stagnant lid, and it might be that indeed the BMO is more likely to survive for a long time. And that would be potentially another way to explain why the core seems light. So we've speculated that in this paper that maybe we see, that InSight might be able to see the basal magma ocean mantle boundary on Mars, but we will see what the results tell us. So these are the take-home messages, and I'll just leave you with that. Thank you for your attention.
Thank you. We've got time for one quick question. If not, I have a brief one. I think this model, you have the iron reduction does that, how much iron, and does that mess up our sort of whole Earth chemical constraints and core formation models for the bulk chemistry of the Earth, or is it so small that it's not?
Yeah, that's a really good question. That kind of depends how fast depends how fast you cool the basal magma ocean. That is, I guess, something you can get constraints for, but also how much basalt or subducted material you kind of pump through the magma ocean while it's cooling. So in a way, you're in this phase here, subducted crust is entering the basal magma ocean, and these gray cumulates are leaving. So you're pumping material through it without the BMO kind of shrinking. It's actually growing a little bit, but it can also. So I think it would depend on this balance between delivery of basaltic material, of aluminium essentially, and the cooling history of the basal magma ocean, which is coupled to the cooling history of the core. Yeah, but yeah, as we don't know the starting point, so we don't really know, I guess, how big was the core to start with when the BMO was still around. I don't think it would mess up any constraints. Yeah.
Thank you. Okay, so we're now moving online, and we're moving to geochemistry.
So Helen, you should be able to start your video now, and you should be able to screen share.
Okay.
Yeah, Helen Williams talked to us about iron, isotopes, and the mantle. I should have said that this session is mantle, this morning was core.
Can everyone see my screen okay?
That looks great, thank you.
Okay, well, thank you very much to the organizers for letting me talk to you about geochemistry today, and particular thanks to the previous two speakers for setting up the problem so nicely. So, as a geochemist, one of the things that concerns me is thinking about what kind of evidence from the rock record there might be for these numerous scenarios of magma, ocean, and silicate differentiation and reservoir formation. And one of the big challenges on Earth, but also on other planets, is how do we actually trace the potential crystallization of really high pressure phases when all we've got access to are very low pressure phases. So for example, how do we try to look at phases taking place in the Earth's lower mantle when all we can access are the very top layers of the upper mantle? And something else that Maxime touched on that I'm particularly interested in is the potential of magma ocean crystallization and phase separation processes in terms of mantle oxidation. And Maxime's introduced disproportionation for you very nicely, so I don't have to. Cheers, Maxime. And this process is basically reliant on the energetic stability or the favorability of ferric iron partitioning into bridgemanite and splitting between iron 2+ and iron metal. And in order to get oxidation of the bulk mantle, what's really critical is that this iron metal needs to be efficiently extracted from the silicate crystallizing mantle into the core. So something I've worked on for a number of years now is using iron stable isotopes as tracers of mineral reactions in the mantle. And my interest in iron stems from the fact that in upper mantle conditions, the partitioning of iron between silicates and melt phases is about 1, such that you're not strongly biased between different phases. And also in experimental work that I did, isotopically heavy iron, so for the non-geochemist, this doesn't really matter. Basically, I just mean high delta 57 iron, is concentrated in bridgemanite, which is enriched in ferric iron, relative to iron metal. such that if we disproportionate iron to ferric iron hosted in bridgemanite, we then lose iron metal, we generate an isotopically heavy, high 57 residue here. And again, critically, in order to see this isotopic signature, we're reliant on separating the isotopically light iron metal from this bridgemanite into the core if we want to resolve this kind of signature here. So again, this was touched on a little bit in Maxime's talk, is how do we find the right samples to look at? So one option that's become really highly publicized in recent years is looking at samples from modern mantle plumes. As Maxime demonstrated, these samples are often characterized by extreme enrichments in primordial 3 helium, and they also have negative mu-182 tungsten. So that's basically recording a time integrated excess of tungsten over the parent 182 hafnium, which would be consistent with a core contribution, because of course tungsten is siderophile and hafnium lithophile, but could also be consistent with, in silicate terms, a melt relative to a crystalline residue, because tungsten is also more incompatible than hafnium. However, modern samples are complicated because we have this problem of trying to resolve core contributions from, say, potential BMO contributions or residual bridgemanite cumulates, for example, and also because of the long-term effects of crustal recycling, which in the case of tungsten can certainly dilute the signature. So a lot of insights have come from going back to a time before there was significant tectonic recycling and focusing on the Archean rock record here. And Archean rocks, you can see from these red symbols here, are characterized by this positive mu-182 tungsten. And this is considered to reflect a signature of very early core formation before the addition of late meteoritic material getting mixed into the mantle. So meteoritic material has a mu-182 tungsten of about -200. So you only need to add a tiny amount here before you can completely erase any signature. And so it's been suggested that these kinds of samples, these very early samples from Akasta, Nuvagatuk, and Isua, with these positive mu-182 tungsten anomalies, would be really good candidates for looking at the mantle before significant tectonic recycling or the overprint of late accreted material. And so here, these are on this plot here of time integrated lutetium hafnium ratio and samarium neodymium ratio. I'll talk you through the axes in a second. We have some examples of these really ancient terrains. Now, again, for the non-geochemists here, the basic point, and this was alluded to really nicely in Charles Edouard's talk, is that there's differential partitioning of trace elements between upper mantle phases and lower mantle phases. And specifically, bridgemanite is capable of fractionating the lutetium hafnium ratio compared to the samarium neodymium ratio. So here it's magnesium perovskite in this older paper here. You can see that the hafnium and lutetium ratio, hafnium is more compatible than lutetium. So that means you're going to grow in a time integrated depletion in lutetium hafnium if you're dominated with a bridgemanite cumulate. And that's in complete contrast to what you might expect in the upper mantle, where the samarium neodymium and lutetium hafnium systems are correlated. So this line here represents upper mantle. Samarium and neodymium isotope systems behave, they're step in step with each other, as the Prime Minister and Chancellor were until a few hours ago. And but we can see here that Isua, northern terrain, is decoupled from this. It's got a massively unradiogenic hafnium isotope signature compared to what we'd expect from neodymium. And that has been suggested to be indicative of equilibrium with a bridgemanite cumulate. So these samples were ideal targets for us because of this decoupled samarium and neodymium and lutetium hafnium partitioning, also because of positive mu-182 tungsten anomalies, and finally because they have positive mu-142 neodymium anomalies, which suggests early silicate differentiation within the first 100 million years of Earth history. And what was exciting for us when we analyzed these samples for their iron isotope compositions here is that we saw a correlation between iron and tungsten isotopes, with the positive high delta 57 iron samples also being the most anomalous for tungsten isotopes. And so without going into an enormous amount of detail, that broadly tells us that the samples that are most anomalous for tungsten are also the most anomalous for iron isotopes. And they have this signature of concentration of isotopically heavy, so high 57 iron into bridgemanite, and the loss of an isotopically light, low delta 57 iron into a metal phase to give us this net isotopically heavy component. And this is pretty exciting. However, when we looked at the trace element compositions of these samples, we found things were a bit more complicated than we expected. And essentially, we get very good relationships in our samples between different incompatible element ratios, which gives us confidence that these ancient rock isotope signatures haven't been overprinted, but they're going in the opposite way to what we expected. So our isotopically heavy iron component that has also got the tungsten anomaly, we would expect this, if it's a bridgemanite cumulate, to have high hafnium and high zirconium relative to elements of similar incompatibility, so lutetium or neodymium. And the opposites observed. In other words, they look more like a melt that's been in equilibrium with residual bridgemanite rather than a bridgemanite cumulate. And so when we were interpreting this data, we started to speculate on whether or not we were actually dealing with a melt that had equilibrated with a bridgemanite cumulate, so some kind of intercumulus melt here, rather than the actual cumulate itself. And in doing so, and exploring these possibilities, we had to start thinking about whether or not lower mantle components could actually be melted in the upper mantle. So these are some models here generated by my collaborator, Simon Matthews. And so what he did is he did a very simple model of kind of trying to think about bulk chemical changes of crystallization in the lower mantle of forming bridgemanite ferropericlase cumulates from a bulk earth KLB1-like starting composition. And then what he did is he explored what would happen to those bulk compositions if you took them into the upper mantle. What would you make? And so for what you would see here is for a pure bridgemanite ferropericlase cumulate, you would make something incredibly refractory in the upper mantle. You'd make something that essentially looks like a Harzburgite. Whereas for a melt composition, at the most extreme 100% melt composition, you'd make something that potentially looks like a peroxenite. And the significance, of course, is how easy that component is to melt, which in turn means how easily we're going to see its signature within the upper mantle. So again, this bridgemanite cumulate is not going to be very visible geochemically at all because it's so difficult to melt, in contrast to some component that largely consists of a melt that's been at some point in equilibrium, inheriting the isotopic signatures of a bridgemanite cumulate. And this is the final point here, is what happens to the iron isotope signature of such a component when you melt it. And the answer is not a huge amount. There's a small degree of isotopic fractionation on melting, which would require another seminar to explain. But the simple point here is that we can't, our bridgemanite signature was something like an order of magnitude greater than this. We can't significantly perturb it with melting in the upper mantle. So I can see I'm coming up for time, so just leave you with some quick conclusions here. From our work on ISUA, we think that we can show that we have some type of component currently melting in the upper mantle, but at some point had equilibrated with a bridgemanite cumulate that had undergone disproportionation. So giving some evidence for an oxidized lower mantle at about 3.7 billion years. Of course, these bridgemanite cumulates, hypothesized bridgemanite cumulates, are not easy to melt in the upper mantle. So that means we have to have some caution with interpreting geochemical signatures. Whether an absence of a signature doesn't mean that it doesn't exist, but possibly we just couldn't melt it. And I guess finally, I thought, given the audience here, it would be interesting to speculate about other planets. Of course, we know that many planets are far too small to stabilize bridgemanite, but disproportionation has been proposed both due to the stability of iron, first of all, in majorite, so at about 18 gigapascals, and even in silicate melts at high pressure, where ferric iron is favored due to its increased compressibility. And so this means that if we can efficiently segregate iron metal to a core, which is obviously more difficult at shallower depths, we do have a potential for oxidizing the mantles of smaller planetesimals. And this is clearly of interest as we start to be able to look at more planetesimals, both from the exoplanet inventory, potentially using atmospheres as a probe for planetesimal composition and oxidation state, and indeed potentially for sample return. And below, I've just got one of the exciting images that came out from Jezero crater this year, where it was revealed that there was an awful lot more olivine in Jezero crater than had previously been thought. So I'll leave it there, and thank you all very much for listening.
I think we've got time for a question or two.
Yeah, hi Helen, this is Maxim. I was just wondering, there was also the suggestion that the anomalously high, so the positive anomalies of the 182 tungsten in the Achaean were related to mixing in of a late veneer, and that the proto-Earth basically, or the, I should say, primitive Earth has a anomaly close to zero. What do you think about that, and is that consistent with your?
Sure. So if I hop back a little bit, so the idea is that the earlier that core formation, if it happened within the first 45 million years of Earth history, when 182 hafnium, the parent of 182 tungsten, was still alive, that should have yielded a mantle with a very slight excess of mu 182 tungsten. And that's what we see in the very earliest lunar samples. But then the addition of meteorite materials, this late veneer, because it's metal rich and it hasn't differentiated, it's got a huge deficit in mu182 tungsten. It's about minus, I think chondrite's about minus 200. So what you're going to do when you add that material in is you're going to bring your mantle down towards zero. And so most modern terrestrial samples, apart from the plume basalts, which here have some of these very negative values, most modern samples have zero compositions, and the decrease is about, give or take, it's about 2.8 billion years, and it roughly correlates with an increase in the abundance of highly siderophile elements, so platinum, iridium, osmium, that would also be hypothesized to come from a late veneer or addition of late accreted material.
I actually thought there was a paper that says the opposite by Brasser and Moises and co-workers, that the late veneer, which was, well, earlier on than we have any samples, caused the high anomalies, and then mantle mixing brought it down to zero.
So I don't know, I can't remember when that particular paper was published, but generally the late veneer is to carry a negative mu182 tungsten because it's so iron rich. So if anything, it wouldn't increase the tungsten isotope signature, it would decrease it.
Okay, thank you. I think in the interest of time, we should move on to, well, thank Helen again, and then move on to the next talk.
If you'd like to stop sharing now, Helen, that would be great.
Yep, I'm doing it.
Perfect, thank you. Won't forget to start sharing this time.
So we're now moving on to core-mantle, mantle-core interaction. Hannah Rogers, we're going to talk about investigating regional heterogeneity at the core-mantle boundary and its impact on outer core flow. Once we've found the slides and started sharing and all the other newfangled hybrid meeting tasks.
Okay, here we go. Okay.
Yep, great.
Great.
So yes, I'm Hannah Rogers, and I'm going to be talking about investigating regional heterogeneity at the core-mantle boundary. I get that banner to disappear? Probably not. Yeah, so I've just moved to Grenoble as part of the Graceful project, but I'm going to be presenting some work that I defended for my PhD earlier this year with Kathy Whaler and Kieran Began. And I would just want to say a special thanks to Elaine Plattner, who provided some of his functions for us to use. So going back to absolute basics, there's quite a lot of geochemists in the room. So the Earth's magnetic field is changing, and we often hear about kind of reversals, so these longer term reversals, but the Earth's magnetic field is changing every year. And we can also see very rapid changes in acceleration that we don't really fully understand. So first takeaway point is that the Earth's magnetic field is changing, and we can use this to look at what's happening deep inside our Earth. And since 2014, we've been using this trio of satellites called SWARM to take really high quality data measurements. And this has really illuminated a lot about the kind of dynamics that are happening in the outer core and provided a lot of information for us. So on the left here, we can see in the background how the secular variation, so the first time derivative of the magnetic field, is changing. And we can see that it's very stable. It's just changing a little bit over time. But the blue circles that are dotted across the world there are what we call geomagnetic observatories. And these are the data sets that I've been using. So every time your satellite passes through a cylinder that we draw on the surface of the Earth that's projected upwards, we can normalize it to kind of a central point. And this allows us to treat our satellite data as if it was a ground observatory. So we can use kind of various methodologies to then study how the magnetic field is changing and what that means for the dynamics in the outer core. So I just hinted at this, that we can relate the magnetic secular variation, so how the magnetic field is changing with time, to core surface flow. And this is called the frozen flux assumption. So we assume that our field lines are tied to packets of liquid at the top of the core here. Sorry, this mouse isn't very good. And as we watch our field lines move, we can infer what the flow is doing. And mathematically, this looks a bit like this, and it's so we have a regularization term, and we can do an inversion. So today I'm going to be talking about models of secular variation, but we can also look at flow models by adding in an additional matrix here called the Gaunt-Alsasser matrix. So usually we represent these models with spherical harmonics because they allow a lot of benefits, such as allowing us to take measurements at satellite height or crustal height and then consider what the model might look like at the core-mantle boundary. They're also very complete and allow for interpolation across the globe, and they're compact, so it represents a lot of information in a very small number of coefficients. But what we found is that these are very poor at regional separations because you need such a large number of coefficients to represent the intricacies of some of our regional features that we're interested in studying. So we've touched a little bit about these features of LLVPs, and these are areas of low seismic velocity at the base of the mantle. And one of the motivations for this work is to kind of not make any assumptions about the temperature difference or the compositional difference, and just have a look at what these features are doing to the magnetic field and the flow underneath them compared to outside of those regions. So my PhD was focused on this technique called spherical Slepian functions. And on the left here is an example from the crustal magnetic field from my supervisor, Kieran. And basically, it is a way of separating models that you can represent with spherical harmonics into individual regions. And the benefit for using these is kind of seen on the right here. So if we have the global magnetic field, but we want to represent this anomaly in the blue circle here, then we need 5,027 spherical harmonic coefficients to represent the global model. And we need 4,181 spherical harmonic coefficient to represent just the coefficients inside that circle. Meanwhile, we only need 41 significant Slappian functions to represent that signal. So we've really reduced the number of coefficients that we would need. They also have, so they're constructed by considering optimizing the amount of energy inside the region orthogonal to the sphere and the region edge. So we keep a lot of the benefits of spherical harmonics, but with the additional information of the region complexity. We can also translate between spherical harmonics and Slappian functions. It's a linear transformation, so we can do a nice, easy check. So we create this G matrix by the optimization of our signal into the region, and then we rank our functions by all of our function energies concentrated inside the region to all of our energy is concentrated outside the region. And so by adding, like, you can look at the amount of energy over your function numbers to see how much they're contributing to the patch. If you use all of your functions, you're going to perfectly recreate your spherical harmonic solution, but you're going to have lots of signal outside of your region as well. So we often kind of have this cutoff point here where things that are above this line we would use to describe inside our patch because they're contributing more than half of their energy to inside our region, and things below this line would be representing outside of our region because those are contributing more energy to outside of the region. So here we have our spherical harmonic global inversion. So this would be the normal inversion that we would do, but then we've looked at it in terms of our inside and outside of our LLVP regions. And we can see that we've done a pretty good job. So we've managed to kind of capture these kind of features, and there's not any signal outside of the region. But we have this like slightly patchiness associated with it because of various problems with damping. But in all, it looks like we've done a pretty good job. We can also compare our spherical harmonic inversion to the sum of our inside and our outside, just as a check to make sure that we're not adding significant or losing significant information during this process. Spectrally, this decomposition looks like this. So our black line is our spherical harmonic model for our global spherical harmonics. And we've got our inside LLVPs, which have a much lower energy in the secular variation. And then we have our outside LLVPs and the sum slightly higher. We've got quite a lot of aliasing at the end of our spectra. So if you can think, this technique is almost like a 1D Fourier series, but on a sphere. So we're probably not capturing some of the complexities of either the region edge, or we're having various problems kind of like towards the end of our limit of our data. Yeah, something I should have mentioned when I talked about measuring our data is that because we downward continue such a large way, we are limited to kind of spectral degree 14 for our models. So that's a real major limitation with trying to investigate these regions. The crustal solution is as good as it is because that goes up to degree, I think, 133 in that particular model. So we have a much less data to kind of try and shape into our regions. So if we move on to looking at the core-mantle boundary, so we've got a kind of more smoothed out signal at the Earth's surface because the complexity kind of gets blurred out between where the field is generated and our observations. We first look at it and we think we've done not too bad a job. We've got kind of blotchy patches on our surface that maybe you could say line up. And again, we've got our spectra here. But one thing I really wanted to point out is the fact that if we take our spherical harmonic solution and minus our sum decomposition, we end up with a map that looks almost as if we haven't done any kind of separation at all. And we've done quite a lot of work trying to investigate how we can best use these functions at the core mantle boundary, but we've not found necessarily the best way to do that yet. And the reason for that is when we perform the separation, can I move this? So this first column here is our classical Slappian functions, and then we have various amounts of downward continuation associated with those. When you downward continue your functions to investigate things at the core mantle boundary, you're blurring your separation out into outside of those regions. So you've just lost the separation that you've tried to incorporate by using these slightly more intensive mathematical methodology. So I guess this is a problem that I'm trying to say is we haven't solved it completely yet, but something that we can also begin to look at these things over time. So again, this is looking at the secular variation at the Earth's surface over time. And we're just going through the swarm era now, and it's very similar all the way through. And hopefully I have convinced you that we have managed to start looking at time series of these Slappian function separations. And we can plot how those spectra change over time. So we've already said that these core mantle boundary ones are maybe less reliable, and they seem very, very stable. So our regularization is quite a big factor in that. But at the Earth's surface, we're seeing kind of this oscillation sometimes in our spectra of kind of starting. So this is June 2015 is our darkest blue, and then it kind of seems to almost oscillate. And we've actually extended this to kind of beyond the swarm era to look at all of the last 20 years of satellite data. And we've also started to look at COVOBs, so a geomagnetic Gauss model going all the way back to 1870. And what we can see is, this is more for the magneticist than anyone else, is that when we divide our proportional energies by our spherical harmonics, we can see that there seems to be some kind of correlation between these LLVP structures and jerks, these rapid changes in magnetic field. How robust this is going to be moving forward, I think, is like a real question we need to kind of look into. So what effect are these regions having on the magnetic field? Still is quite a big and open question, and hopefully we'll put some more time and energy into looking at regional magnetic fields in the future. So the main conclusions I had from my PhD was that, yes, we can incorporate spherical Slappian functions into inversions to look at core surface at secular variation separations, but mostly at the Earth's surface. When you have that additional downward continuation to the Earth's core, we have much more complicated issues. Also, adding that additional matrix that turns our secular variation into core surface flows is very, very difficult. But again, for the geochemists out there, I would say that the magnetic field has like a real way of us allowing to look into the dynamics at the top of the Earth's outer core, and maybe trying to understand those interactions and what that means physically from direct observations. So hopefully more work to be done in the future. So great, thanks.
Thank you, Hannah. I think we've got time for a question or two.
This is just from me. Maybe you can speak a little bit more about the link between LSVPs and magnetic jerks. Do you have any idea what the what some mechanism might be there, rather than just sort of observational linking?
In a word, no. I mean, Richard can probably. So the thing is that when we've looked back, and you don't know a jerk is happening when it's happening. It's only when you look back in the magnetic record that you know these things have happened. And there's some very large jerks, but some of them are only just being found going back and looking through the literature. Now we have this higher quality data set from SWARM. Some people have linked them to waves across the core-mantle boundary, and that is the dominant feature right now. But then if you put something on top of your core, which is different, then how is that going to affect your wave? We don't really understand yet. So there's lots of open questions, basically.
So we've got one online from Sheila Peacock. I assume that downward continuation is prone to exaggerating small variations in the input field. Have you done sensitivity checks on this?
No, I haven't, is the honest answer.
One to think about for the future, maybe.
So can you just jump back one slide? I was trying to get my head around I guess the longest timescale, the right-hand side.
Yeah, so these grey bars here are periods of these, what we've called jerks. So these are identified in the literature from various people. So these are areas of rapid magnetic field acceleration change. And we just found that it was odd that these seem to correlate with certain timings. Whether they are true representations or not, we're still exploring. So I don't know.
So so the deal here is, if you look at the sum on the right hand side, if you look at sum composition, there's no obvious link between the grey bars and the red line. So, but once you decompose it, and therefore it's telling you something.
In the spherical harmonic inversions, we see these acceleration changes. So when you divide by those acceleration changes, you shouldn't, or when you normalize to your spherical harmonic, you should be getting flat lines in theory, because you've accounted for them by normalizing it to your spherical harmonics. But for some reason, these areas of under and outside of these LLVPs seem to be correlated in some way. But again, this is very questions to be answered. Richard, probably.
The figure's a good start, but don't sweat the details particularly. For example, you note how everything gets much more regular and intense on the right-hand side. Modern satellite era started in about 1999. This may not be entirely a coincidence. If I was going to stick some lines in there, I would stick one in certainly 1981. I'd certainly stick one in 1971. You pays your money, you takes your choice, depending what you believe. So it's good. It's a very good thing to do, but don't overinterpret.
Okay, something for me not to worry about. So let's thank Hannah again. And can we thank Fred as well, who's carried most of the work of organising this meeting. And will now tell us what we need to do.
Okay, yeah, I think if we could thank all of our speakers, especially the invited speakers, one more time. And that's the end of the talks today. So we've got another half hour up in the library to look at the posters and just have a mingle and a chat. And at the same time, we've got tea and coffee and refreshments, the same place as this morning in the Linnaean room. So yeah, thank you all so much for coming. It's been a really great set of talks, and yeah, enjoy. So thank you everyone online. We'll be closing the meeting now, but thank you very much for your attendance. And thank you for the remote speakers as well.